Good morning and welcome to day 2 of the CubeSat workshop. It's wonderful to see you all back here. Hopefully you enjoyed the social event that we had last night and didn't need to sleep in and are here now. Anyway, so I'd like to start with a couple of announcements and reminders. First off, a thank you to all of the sponsors who make this event possible for us. We also have a few special events going on today. Max IQ is holding hands-on workshops in the back of the pack that you can attend to learn more about, how to use their technology. We have a talk at 1 p.m. by Blue Canyon's Graham Gable, presenting on the company's capabilities as an end-to-end spacecraft provider, and that's going to be over in the pavilion, which is the same level here, but over to the left. You can access the pavilion by going to the check-in station and walking down the stairs there. Today, we're also providing tours of the CubeSat lab here at Cal Poly. You can sign up for those tours at the check-in station as well, if you're interested in that. I believe there's a few times that the tours leave, but I don't know what they are. So check in with the station up there. At the check-in station, we also have the Hawaiian shirts. If you're interested in seeing what the designs and patterns are, you can go up there, and if we have any more inventory in your size, it's there for sale. Let's see, have I made it through everything yet? No, okay. Second floor has a lot of exhibitors on it, so make sure you get up to the second floor and check out the exhibitors. Third floor has posters, so during breaks or in between sessions, please make sure you go up and check out the student posters and the other posters up on the third floor. Like yesterday, our lunch is going to be a few buildings over. The official name of the building is the Multi-Activity Center. If you had lunch yesterday, it's the same place. If this is your first day or you didn't have lunch there, follow the crowd. You're going to have to go over to the left a couple buildings past the sand volleyball pits to find that building. Okay, for the presenters, if you haven't submitted your presentation or you need to update it, please visit the registration table up in the lobby and they can help you upload a new version of your presentation or the original version of your presentation. Okay, so with that, our first speaker today, or our keynote speaker today, is from Millennium, and we have a short video that we're going to show you about Millennium prior to me introducing the speaker. So we'll just jump into that video.
Curious, bold, clever. That's who we are at Millennium Space Systems, a small satellite company that is fast-paced and innovative, building satellites in months, not years. Our team comes up with clever ways to revolutionize space. We take risks, challenge the status quo, and embrace commercial technology. Because the missions we support matter, our work safeguards what's important: people. And when we launch and operate our satellites, we know each one of us made it happen. At Millennium Space Systems, you have the opportunity to grow your career in the direction that's right for you, in an environment that's open, inclusive, and collaborative. Are you ready to help accelerate the small satellite journey to space? Join us, channel your skills, and contribute to a greater purpose.
So it's my pleasure to introduce Doug Holtz. He's our keynote speaker this morning. Doug's a space mission program manager with Millennium Space Systems. He's a leader in complex proposal campaigns, including technical approach, pricing, and review team support. He has more than 15 years of experience in the aerospace industry, and perhaps most importantly, he's a Cal Poly alum. So if you would please welcome Doug.
Awesome. Thanks, John. All right, thank you for that. Like I said, my name is Doug, and I'm so excited to be here today. And especially the theme of building the future of space together. It's exciting. And so the title of my talk today is Cubesats and Cocktail Napkins. And I think that cocktail napkin connection should make sense here in just a moment. But like John said, I'm a Cal Poly alum. I studied manufacturing engineering here, and it's always great to be back in town. Love being back here, and I love the engineering program, and if I'm being completely honest, though, I think my favorite class was probably bowling. But seriously, I'm so happy to be here and to be able to share my passion for innovation in the space industry and why I think it's important and how CubeSats fit into that. So first, a little bit about why I'm passionate. So let's rewind the clock a little bit. I got my first job out of college, actually just at the Fall Career Fair here on campus. And it was there at a large aerospace company that I really started to learn the basics about the space industry. I was a manufacturing and test engineer working on some large satellite propulsion systems. And I spent about 10 years there working various roles. And it was then that I moved to Millennium Space Systems, which is where I'm at today. Now, a little bit about Millennium, a little more than what the video said there. We were founded shortly after 9/11, with our founder really saw a need for a rapid space capability geared specifically toward, or primarily toward, the national security space market. Now, it was a really small company back then, and when I joined, it was about 100, just over 100 people. And with a company that size and with the kind of work we were doing, we all had to be involved in pretty much everything. You know, we all had to wear a lot of hats. And I found that in that role, I was no longer a small part of a big machine, but I was really able and obligated to be involved in pretty much every part of our satellite's development. I quickly had to learn not just about our systems, but about the satellite industry as a whole. And for me, that was the trigger. That was when I became passionate about the space industry. And Millennium really helped me to develop an understanding of small satellites and really what their value in space development is and how they actually were helping to enable even those really large programs that I'd been working on in my prior jobs. And Millennium's niche in the industry is really being able to quickly pull together high-performing small satellite prototypes and constellations. And we really have the capability to be agile and low cost in a way that traditional large system development just doesn't. And the work that we do really matters. Now, before we start talking about CubeSats specifically, I want to briefly touch on just the broader space industry. So the space industry as a whole has become incredibly important. I don't think a day goes by where every single one of us doesn't interact with space in some way. So GPS is probably the easiest example of this that I think we can all wrap our heads around pretty easily. Our phones, our cars, even our bank transactions all rely on GPS positions or precision timing. Other things like global communications, weather forecasting, all of these would be nothing like they are without today's space-based infrastructure. And national security is another really key example of why the space industry is so important. The threats that our nation and our allies face on a daily basis are constantly evolving, and we need rapid advancement and innovation across the industry if we're going to stay out in front of these threats. Now, it's this rapid advancement and innovation. This is where CubeSats and you fit in. So CubeSats are a pretty amazing platform. They're inexpensive, relatively speaking. They're quick to develop, and they become pretty easy to get up into space with, you know, some of the modern launch methods and ride shares and such. And while they may not be big enough for all of the missions out there, they are perfect for fielding new technologies and testing new ideas. Now, this is where I see such a huge benefit from CubeSats and where the concept of the cocktail napkin comes in. So a little story, a couple of years ago at Millennium, we had just finished the production of the third and final vehicle in a small-sat constellation that we were developing and operating for one of our government customers. And the program, though not strictly a CubeSat, was a small sat whose mission was simply to demonstrate some new technologies and to do so quickly and efficiently. Now, the first satellite at this point had been in operation for about 6 or 8 months and had been really generating some pretty phenomenal data. So I was at Kennedy Space Center with my government customer, and we had just unloaded the third satellite, like I mentioned, that we had just finished developing. Just unloaded that third satellite from the truck. And we were standing over the crate. We're just kind of killing time, waiting for some final paperwork to get processed. And we started discussing some of the data that we'd been getting from that first system, and really talking about what were some of the possibilities that demonstration was starting to open up. And the next thing you know, right there on top of that satellite crate, we started sketching on the proverbial cocktail napkin an idea, a concept for a next generation system based on this new technology. So at that point, an idea was born. And I realized that's what this small satellite demonstration was. It was a small satellite. It tested a single idea. It did it quickly. It did it inexpensively and effectively. And this turned into a concept that really started addressing real-world hard problems. So using the technology that we demonstrated with that small satellite, we are now at Millennium working on systems that are revolutionary and are advancing our nation's capabilities. So these next-generation systems, we can trace those right back to that first small satellite demonstrator. So CubeSats and cocktail napkins. So CubeSats are pivotal in driving innovation. And that is why I'm honestly so excited to be here at this workshop today. So Cal Poly, you all know this, but has pioneered CubeSats, and they're really emblematic of the learn by doing philosophy that Poly's famous for. And in the same way that students here learn how to design and build satellites through the CubeSat programs, the space community is able to learn by doing with the capability of being able to test concepts in space at a relatively low cost. And while they are a great way for students to learn about the fundamentals of satellites while in college, CubeSats offer the broader industry so much more. So the space industry is traditionally really expensive, and especially when it comes to developing systems for the government. So building new satellites can take years, sometimes even decades, and they have to work perfectly once they go up where you've potentially blown $1 billion. And there's so much at stake financially in some of these large traditional systems that the amount of testing and certifications and paperwork is astronomical. And it really makes things move at a snail's pace. But with CubeSats, we have the luxury of learning by doing. With less risk and a lot less cost, CubeSats really break the mold of how things have typically been done. They let us experiment with new ideas and technologies and push space forward. You can learn quickly, even fail quickly, learn from it, and move on. A good example of this is a program at Millennium that we did recently called Drag Racer. And this was an 8U CubeSat. It was a program that was developed to demonstrate a new method of space debris removal. So this was a really simple 2-satellite experiment that tested the use of a deployable tether to cause a LEO system to deorbit faster due to increased aerodynamic drag. So a simple concept, but the results were really quite amazing. The CubeSat with the tether was able to deorbit about 500 times faster than the one without. So this small program quickly demonstrated and qualified a technology that can now be added to any other LEO system. And just by adding this technology, we can now deorbit satellites at the end of their mission life much, much quicker and really help to address the very real issue of space debris. And by doing this as a targeted CubeSat demonstrator, we were able to develop this technology without any risk to a more critical mission. So CubeSats really provide us with a platform to quickly mature technologies for the broader industry. So 2 more ways that I see CubeSats serving as a platform to test new ideas are the infusion of technologies from other industries and the demonstration of new processes, new methods, and new standards that can be adapted and applied across the industry. So there have been so many technological advances across so many industries recently, And CubeSats give us the opportunity to leverage those in space. So let's think about the boom in self-driving cars recently, right? Think about that problem. The multi-sensor data fusion and real-time processing necessary for the self-driving car problem is directly applicable to so many really complex space missions. So on one of our more recent programs at Millennium, we're leveraging some new processing technologies that are targeted and geared directly at this self-driving car market. So being a leader in prototyping small satellites, along with our ability to rapidly space qualify commercial technologies, gives us the ability to really translate these new terrestrial advancements directly into space capabilities. So using technology developed in areas outside of aerospace is a fairly new concept within the space community, and one that really allows companies like Millennium to provide the most tech-refreshed, affordable, capable, and reliable solutions to fit our customers' needs and our customers' missions. And CubeSats, so CubeSats provide us with a fast track to space demonstration of technologies from other industries. So another example, also from the automotive industry, are batteries that we use in our satellites. So batteries are obviously hugely important to a satellite. They're kind of the heart of the system, storing the energy and delivering to all of our subsystems. And the batteries we use in our small sats are the exact same cells you would find in your electric car. And we just take simple cells, put them in strings, build them into an assembly and integrate right into our systems. And this has become a really standard way of doing batteries in CubeSats. And this application of terrestrial technologies has crept now into larger systems. So with larger systems, we're now just adapting this exact same approach. So the result is a streamlined product for the entire industry that's demonstrated and enabled by CubeSats. And while we're on the topic of batteries, I have one little story. The most fun I ever had with batteries was when we had to demonstrate a few years ago the suitability of one of our battery packs for flight on the International Space Station. So we had to be able to prove that if one of our battery cells exploded, it wouldn't cascade into a failure of any neighboring cells and then present a real hazard on the space station. So after some analysis, we decided that the best way to accomplish this was to take a drill press and drive it right through one of our battery cells. As you can imagine, the resulting explosion was impressive, and it's always fun when you get to blow stuff up. All right, that's kind of engineer's dream. But I digress. The other advantage of CubeSats that I mentioned is the demonstration of processes, or methods, or standards. And as a good example of this, I'll pull on the PPOD standard, the Poly Picosatellite Orbital Deployer. Is a CubeSat deployment system. It makes it so that anyone developing a CubeSat conforms to a common set of physical requirements, and the result is universal compatibility with the deployer. So obviously, I'm sure you all know about this because it was developed right here. And a huge shout out to everyone instrumental in that, because this is really the type of innovation that CubeSats demonstrate. So in the aerospace industry, we really need now more innovations like the PPOD standard for the next generation of satellites. So a new open standard would be hugely beneficial. So instead of every satellite manufacturer having their own locked system, we could have one standard for launch and deployment interfaces, and maybe things like refueling or even repairing satellites. So another way that the space industry can learn from CubeSats is the approach to system development from a risk standpoint. So far we've talked about the technologies demonstrated by CubeSats and enabled by CubeSats, and that's kind of the what. But what about the how? So in traditional system development, we tend to be very risk averse, and I think anyone who's worked on any major systems has experienced this. But this mentality is really driven by the scale, the importance, kind of the criticality of what some of those traditional large satellite systems represent. We have to know that they're going to work. And when that much is on the line, a really conservative approach is understandable. But the problem is that this traditional mindset and kind of culture of risk aversion tends to stifle innovation and really burden our development process. So here again, we can learn from CubeSats. So the typical risk posture of a CubeSat developer is vastly different from the traditional large systems. CubeSats thrive in a pretty risk-tolerant environment because of their quick development cycles, relatively low complexity, and often less strenuous mission requirements. You're able to accept the potential consequences of some system risks. So things like single-string architectures, maybe new or unproven technologies and new materials, all of those become a little more palatable. But in executing CubeSats programs with this kind of increased risk tolerance, you're very quickly proving out technologies, mitigating those risks associated with new technologies, and proving out new and innovative approaches to system development. So things like design approaches or test methodologies. And then taking those experiences from CubeSats to the broader satellite industry opens up potential opportunities for new innovations beyond just CubeSat programs. So what should be crystal clear, hopefully by now, is that CubeSats have a dramatic impact on the space industry. So CubeSats let us test new technologies. They provide us with a model for a quick refresh of new hardware and software from other industries, with lower risks, lower costs, and accelerated timelines. And they also provide us an example of new and innovative approaches to satellite development. And while not all missions can be accomplished with CubeSats, or even small sats for that matter, they do fill an ever-increasing role in driving innovation across the industry. And best of all, this is within your reach right now. CubeSats and the ability to try new things, to learn by doing, it gives you the ability to experiment, to create the next great leap in innovation. And for any of the students out here, it gives you the skills on your resume that we're looking for in the satellite industry. So CubeSats and smallsats both give us the ability to jump in, to be involved in innovation and make a difference right away. So at Millennium especially, it's exciting, and you can find yourself in situations and in positions that you just wouldn't expect. So another story, I mentioned earlier an experience with the International Space Station. Well, once when one of our satellites was being deployed off of the space station, we were watching a live video feed of astronauts on the space station unpacking our satellite and prepping it for deployment. So as we're watching this, it was live, it was real time, but we had a video feed, but we didn't have any audio, so we couldn't hear what was going on. But watching the whole time. And at one point, I saw one of the astronauts look up at the camera, and it looked like he said something, like he asked a question or something. Well, just then my phone rang, and it was the ops room. And they asked me a question about the system. I answered the question, and then watching the video feed, I saw the astronaut nod his head in acknowledgement and move on. And I never would have thought that I'd be answering a question in real time from an astronaut on the space station. So CubeSats open up some pretty cool opportunities. So the industry is experiencing tremendous growth. Small satellites are in huge demand for both commercial and government missions. And we need engineers to help us with those missions. And specifically, we need engineers who can think outside the box and bring that spirit of experimentation that is bred in CubeSats. So if you're interested in learning more about the work that we're doing with small satellites at Millennium, I'll be at the booth later. Come and talk to me. Come talk to some of our other Cal Poly alum who will be there with me. And let's build the future of space together. And Thank you. I want to thank you. That's pretty much all I've got to say, but I want to thank you so much for the opportunity to be here. And hopefully you all are as excited about CubeSats and about the opportunities that they present as I am. And again, for students out there, I hope you join us in the small satellite industry. And for everyone, grab a cocktail napkin and sketch out that next great idea. Thank you.
All right. Thank you very much, Doug. So next up, we have a short break. So please enjoy the snacks, enjoy the posters, enjoy the exhibits, and then we'll reconvene here for the next session. Thank you.
everyone. I hope you had a good break. So we're going to have another speaker on very soon. We're getting him set up right now. We'd like to thank Experior Labs for providing the coffee and snacks. And we actually have a sponsor video for them that we'd like to show you now. All right, people backstage, pull up the sponsor video. All right. So our presenter next up will be Kyle Johnson from the University of Nevada, Las Vegas. Please welcome him.
Hi, everyone. My name is Kyle Johnson from the University of Nevada, Las Vegas. I'm an undergraduate researcher with the Security Science and Engineering Lab there. Today, I'm going to be presenting a long excursion 12 DOF CubeSat design test platform with optical sensors. It's kind of a lot to unpack there, but we'll get through it. All right. So this is our platform here. So the purpose of this platform is to test RPO for a pair of CubeSats. Our current capabilities and characteristics, we have 12 degrees of freedom, optical sensing capabilities, we have a 2-meter range. We built this in 3 phases, which I'll go over a little bit. We've built it with commercial off-the-shelf components, which is important for us for budget purposes. With those COTS components, a lot of those came with their own software, so we developed an in-house Python script to integrate everything together. So a little backstory on why we did this. We were approached by the Jet Propulsion Laboratory to create a test platform for some RPO operations for some CubeSats they wanted to develop. So they wanted it to have 12 degrees of freedom. They wanted it to simulate microgravity as best as you could, being in a lab on Earth. And so we got to work. We had an idea in mind where we wanted to use a pendulum model to create our microgravity. So once we had our design in place, we started pricing out parts to build this thing. We got our bill of materials and everything, and we quickly found, like maybe some of you have found before, that a lot of the stuff that you can find out on the internet is pretty expensive and maybe a little cost prohibitive for the budget that you have for a CubeSat project. So we started thinking, can we go to common online vendors and find parts for the mechanical structure, for the movement of our test platform that will not be so cost prohibitive and be accessible to other groups. There we go. So like I said, we built our test platform in 3 versions. This is version 0. This was our first iteration. Version 0 uses an inverted CNC router, which we bought off Amazon, and we use the stepper motors on that router to give us our translational motion. We then took out the router portion of the CNC, mounted a camera gimbal to it, and you can see we mounted a CubeSat to that, and that gave us all of our rotational motion. Version 1, which is the one that I'm going to be talking about the most today, this is kind of where we're at our current phase, is a very similar idea. We took a lot of the things that we learned off version 0 in terms of integrating software and kind of inverting that CNC and stuff, and we mounted that on a ball screw and 2 linear rail guides to give us 2 meters of motion there. We also attached another camera gimbal to that CNC in the same way that we did with version 0. And that gave us 2 meters of longitudinal motion, 300 millimeters of transverse, and 45 millimeters of vertical. The CNC has very limited vertical movement, but we were able to get 3 axes. With rotational motion, like I said, we have the camera gimbal there. For our roll, we have plus or minus 30 degrees. For our pitch, we got from minus 90 degrees to 145 degrees, and we have a full range for yaw. Our test nodes are the version 1 and version 0. So the version 0 is stationary on one side of the test platform, and version 1 travels to and from version 0, and that's currently how we're getting how we're testing RPO. So our software for this, our CNC stepper motors are controlled by a Python script where we enter in Cartesian coordinates. It converts that to RS-274, which is G-code commonly used for CNC applications. And that goes to a GRBL board, which moves those motors. The motor attached to the ball screw is controlled directly by the Raspberry Pi, not by the GRBL board. And the gimbal is controlled through a macro that interfaces with the gimbal's Android application. We use a LiDAR sensor and a camera for our optical sensing, and the camera runs on its own, but it feeds information to a Python script that then informs a test platform on where it should move. The LiDAR sensor is controlled directly by the Raspberry Pi. So for our LiDAR module, we're using Garmin LiDAR Lite version 4. We like this sensor a lot. I should mention that we're using LiDAR and cameras because we have a version 2 coming up that we're developing. And the idea is in our ultimate version of the test platform, when you have somebody's cube satellite internally trying to determine where it's at position-wise, that we have optical sensors that are also verifying that information. So we're developing our optical sensing for those purposes. So just some quick characteristics of this is we've got a beam divergence of 4.77 degrees. It's a near-infrared LiDAR sensor. It uses near-infrared LEDs. And the range is from about 5 centimeters to 10 meters. So it gives us, for our test platform, we're only going to 2 meters. It works pretty well. And we use an I2C protocol to communicate with it. Pulse width is 1 microsecond with a period of 59 microseconds. And you can see that for our range readings, it's pretty accurate. It's got a little bit of an offset of about 1 or 2 centimeters. And right now we're using a Canon EOS M50 for our camera. It's got 24.1 megapixels. Really, the reason we decided to go with this right off the bat is because it has auto tracking capability. The way our Python program works at the moment is the camera displays on its screen what the position of the camera is, and our Python script reads that, and that's how it sends the information to our test platform. So moving on, version 2. This is in development right now. This is our pendulum idea I was mentioning before. Version 2 is also going to have 12 degrees of freedom. So you've got your 2 nodes. Each node has 3 degrees of translational motion and 3 degrees of rotational motion. So there's your 12 degrees of freedom. It's going to have multiple cameras, multiple LiDAR sensors to really zero in on that positional data that I was mentioning before. It will use induction sensors to read the deflection of the pendulum. And when those sensors sense that deflection, we have stepper motors that will move the CubeSat in that direction to give us a little bit of sense of, let's say, for example, you have 2 CubeSat satellites that hit each other and bounce off each other. It'll travel backwards and they won't just slap together over and over. That's not good. So this one will have a passive gimbal we'll use. We are currently assuming that whatever CubeSat satellite that we are testing has some sort of internal way of attitude control, of controlling attitude. And the test nodes on this one will be the version 1 that I just mentioned and this version 2 module. And with that, that's the end of my presentation. Does anybody have any questions? If the 2 satellites, our plan is that right now is that the Cube satellites will communicate to the test platform itself to kind of so that we can get it to move where it wants to go. I guess if they want to communicate with each other and send the test platforms some different information, we'd be open to updating our design to something like that. Does anybody else have questions? All right. Well, thank you very much. Hope you guys enjoy the rest of the conference. Thank you. Yeah, good. Good job. Okay.
All right, thank you very much to our previous speaker, Kyle Johnson. Next up, we've got Michael Pham from the Blue Dot Consortium at Cal Poly Pomona. Please welcome him. There you go.
Thank you. Hello, everyone. Good morning. Wow, that is a lot more reverb than I thought I was going to get. It's going to take a little getting used to. But yes, thank you for all coming out this morning. This is my first, and I'm sure many of your first conferences back in person since the pandemic. So it's still a little getting used to seeing everyone in 3 dimensions, but very happy to be here. And yeah, today I'm here to talk about the Pleiades Rapid Orbital Verification Experimental System. A big mouthful, but we really love our acronyms. And I actually thought I was going to get put in the educational CubeSat talk, but I guess they saw verification and they decided to put me over here in reliability. So I suppose I'll be talking about the reliability of educational programs a little bit. Just as a primer, I'm an undergrad from Cal Poly Pomona in the Aerospace Engineering Department, and Cal Poly Pomona, we do not have quite the illustrious CubeSat history as Cal Poly SLO. So we I started our undergrad program to do CubeSats just about 3 years ago. And we have our first mission, BroncoSat-1, which I served as the chief engineer for, launching this summer on SpaceX Transporter 5. And throughout the process of trying to start an educational program, going through, trying to get our university's first space mission off the ground, what I saw and what a lot of my colleagues saw is really just a lot of problems inherent with trying to do this kind of thing. So what I'll first get into is kind of the current state of what is it like to do in educational CubeSat mission. I'm sure all of you are very familiar with how quickly spaceflight is proliferating. You know, we've seen this twofold increase in the number of satellites put on orbit in the span of 2015 to 2020. But has the availability of formal education into how to do spaceflight increased by twofold in the same amount of time? I would argue no, and I think a lot of people would agree with that assessment. So some of the core struggles, right? I'm sure you've heard about a lot. I'm sure you heard about it yesterday as well from the 1600 CubeSats talk. But although the availability of launch and the availability of mass to orbit has skyrocketed, all of the challenges of doing a CubeSat and doing a space mission are still very, very prevalent. They're expensive. It's technically challenging. Schedule crunch is perhaps worse than ever with the number of launches and how tight launch windows are these days. And there's a lot of institutional knowledge that has to be transferred or derived in the first place for an educational program to really take hold. And there isn't quite yet any kind of centralized information for how to start an educational program, but more importantly, how to maintain a sustainable educational program. How do you take a CubeSat in the education space from just being a one-off, a one and done, to being something that is a core part of the formal curriculum that the industry and the future workforce can expect as a regular part, right, of students gaining experience in how to design, build, test, and fly a spacecraft. The way I sort of liken the industry right now is, imagine if you were a chemist or a biologist and you wanted to do some kind of research, perhaps sequencing some DNA to, find the genetic markers for graying hair or something. Imagine if you were in that position, and before you ran your experiment and collected any data and got any experience, you first had to design, build, test, and verify a PCR machine from scratch by only reading academic papers that vaguely describe what a PCR machine should be. That is what we are expecting of the educational CubeSat space today. So we are trying to introduce a new platform. If you were here yesterday afternoon, you heard from the team from Kyushu Tech, and you also heard from the team from the Hawaii Spaceflight Lab about their CubeSat platforms for education. Both of them open source. We are doing something very similar, where we also are looking at a 1U CubeSat that we're going to be open sourcing, but particularly, I think the different approach that we want to take with this is to, in a sense, design the platform in a way where the end objective for us is not necessarily to make a well-performing, well-optimized spacecraft, but instead we're looking at how to put a lab bench in space, right? The Japanese CubeSat kit, I've gone through the documentation, is incredibly well designed, well optimized. The chances of missing success are very high with using that, but it still costs, $30,000, $40,000 US to replicate. And at that price point, that's kind of like if the aerospace engineering department decided to spend $40,000 a year on something that they're going to send to space and they never see again, that's a tough sell. It's also a tough sell to get into the classroom because you're not going to Like, so I'll be honest, you're not going to trust your undergrads who have never built anything in their lives with a $40,000 piece of equipment. So we are trying to take the approach of making something that can be qualified for space flight, right? It can go to space and behave like a spacecraft, but incredibly low cost and incredibly simple to answer some fundamental questions about the essential challenges of doing something in the space industry, which are: what is a spacecraft? What do spacecraft do? And how do you use a spacecraft? Right? These are sort of foundational pieces of information that we believe are really important to developing a good educational foundation for the future workforce. So getting in a little bit into the hardware aspect, we're going for a backplane strategy. I think backplanes are really where the industry is going. People like backplanes better than like PC-104 for sure. And we are focusing on hardware components that are as much consumer off the shelf and sort of adjacent to the maker sphere as possible. And I know that for the more seasoned engineers in the audience, right, these are red flags, right? It's like, oh, the maker sphere, right? Like, how do you verify all of this? How do you make sure you have mission success once you get to orbit? We see it from a different perspective, where we see it from the perspective that by choosing things that are in the makersphere and choosing things that are simple and do not have a lot of institutional knowledge overhead, we're able to get the students thinking not about how to make their code from scratch, right? Or how to clone a GitHub repo in order to use the custom Linux distribution that is required for their $15,000 flight computer. We see it as the students are getting just a fundamental base level of experience with the core challenges of doing a space mission, right? Command data handling, how do you talk to it? Power systems, how do you keep it going once it gets to space? A structure to hold it all. And then communications, right? How do you do link budgets? How do you understand on an intuitive level, what does it take to have a functioning bare bones space mission? We also have a structure that we think is pretty novel. We're taking an approach where we're trying to have this laser cut and made out of aluminum stampings wherever possible. So we are trying to keep the piece price incredibly low with this entire adventure, where ideally we want to see the raw bill of materials cost for just all of the hardware that goes into this kit platform be about $1,000 US. Because we believe that at that price point, it's something where if every year a department wanted to buy 10 of these, they wanted to buy 20, right? Have their students assemble them, that is within the realm of possibility, right? It's not just going to be the one $40,000 cube that sits in the lab and none of the undergrads can touch because they might break it. When you have 20 and it doesn't cost very much, they're allowed to make mistakes and are allowed to learn with that learn by doing mentality that both Cal Polys try to embody. We're also keeping the software really simple. CircuitPython based. Those of you who are familiar with the PyCubed standard from Stanford University, we're actually a PyCube derivative on BroncoSat. So we really like CircuitPython. I know that many embedded software purists, though, will still want the capability to have embedded C. And so we're trying to sort of bridge that gap where, in our perspective, satellites are a truly interdisciplinary project. And while embedded C is, of course, incredible and really what the electrical computer engineers should be learning and getting their hands on with, spending a year teaching an aerospace engineer how to work in embedded C is perhaps just a huge waste of time. So keeping the software stack relatively simple. Artificial intelligence is also on this slide. That's actually the main tech emphasis from our lab at Cal Poly Pomona, outside of trying to develop this educational CubeSat kit. Not really going to get into it here, but if anyone's interested, you can contact me. I'd love to talk more about it. So the roadmap for us looks as such, where we're currently in the state of prototyping with our initial versions of our electronics and structure. Ourselves at Cal Poly Pomona, along with the Hawaii Spaceflight team, and the team from Stanford, Stanford Student Space Initiative, we are getting on SpaceX Transporter 6 this October for a test flight. And we're hoping to schedule another test flight sometime early in 2023. So we're moving at a pretty rapid pace to getting towards verifying these kits on orbit. And the long-term vision is ideally that we get to a place where this platform is stable enough to where a classroom can run a year-long or perhaps 2-year-long curriculum, and every single year, right, in the classroom, you can have maybe 5 or 9, right, 10 student teams working on these kit platforms, and then you can have one of them, perhaps the best one, or just one built by slightly more professional engineers, sent to space so that the students see both sides of the mission. They see the implementation, they see the test, they see the verification, but then they also get to see the operations, right? Perhaps the most important part of answering, what does a spacecraft do? And most importantly, how do you interact with and how do you use a spacecraft? And yeah, that is about all I have in slides. I'm hoping that next year, when we're back at the conference, I can have some prototype kits to share with everyone here in the audience, and you can take one home and get a feel for it. And if any of you have students, right, get your students getting your hands on it. So yes, I will go ahead and take questions. I think I have a couple minutes for questions. Yes. Yeah. So the question is, what are the students actually learning with the pre-built kit, right? I know that the mentality historically has been, the students get the systems engineering, they get to do the trade studies, they get to pick all the components for the spacecraft, right? And derive a lot of educational value from that. What I would say to that is that as an undergrad myself who went through that process, going into that process, the systems engineering and all the things related to that, to design a spacecraft sight unseen, having never seen a spacecraft before, having never used a spacecraft before, having never even really understood what a spacecraft really is, it's questionable educational value because you're just making a lot of sort of leaps of judgment and leaps of faith. Does an electrical engineer appreciate the oscilloscope any less because they have not designed it themselves? I don't think so. And so I think that what we're going for is like an oscilloscope, but for space. Okay, any more questions? Yes. Sorry, one more time?
What you're talking about, this is about payload. I don't see any reference to spacecraft.
I might not have made it clear in the slides. This is intended to be a free-flying 1U spacecraft, where we're going to have a command data handling system, a power system, and a communication system, along with a 1U structure that is capable of going to space, just as a standalone item. And it's something we are going to send to space this October on Transporter 6. If the students would like to develop their own payload, there is going to be room left over in the satellite for that to happen.
When you send a vehicle to space, you need to learn how vehicle behaves in space. This is what you're saying. There is nothing there telling students that this vehicle goes to space and how space affects the vehicle, how space. Because there is nothing. It could be the car, it could be the ship, it could be anything.
Yeah, so I see where you're getting at here, where just by making sort of a black box for electronics, right, it is sort of abstract, right? That could be a car, it could be a ship, it could be an RC plane. The intent here, though, is that, we still want to try and take the students through all of the steps for qualifying their vehicle for space, right? So vibration tests, thermal vacuum tests, right? These are things that need to be a part of the formal curriculum. And the goal is that these are low cost enough to where, yes, you can have them as sort of black box, educational tools in the classroom, but you're also able to take one of these at the end, already have it pre-qualified through the vibration, the thermal vacuum, electromagnetic compatibility, and then put it on a rocket and get it in orbit so the students can do operations for some amount of time as part of the education. Okay, I think that's all the time that I have. So thank you, everyone, and I hope you enjoy the rest of your conference.
All right, thank you so much, Michael Pham. Next up, we have Chris Maynor from the Mayo Clinic in Jacksonville, Florida. Please welcome.
Hello. Sorry. Thank you so much for having me, and thanks so much for the organizers for giving me the opportunity to present our work here today. You can probably already see from the title, we're looking at cells, so this is a little bit more biology than engineering, but I hope I make it worth your while and maybe spark some interest. Always happy to talk about more offline afterwards, since obviously the time slot is very short. So again, I'm Chris. And I work at the Mayo Clinic in Jacksonville, Florida, so we're just a drive up from KSC, which, is one of the reasons why it's so convenient for us to work in space biology. We are particularly interested in looking into human cells and how human cells behave in space. And you may probably still wonder a little bit, well, why do we care so much, and what's the purpose of these studies? The obvious answer is to study how will astronauts react to prolonged space flight. But I dare tell you that very few of us will become astronauts. I've tried. And so it's a very, small group that this may be affecting. However, many decades now of biological research in space have shown that there's a great value that can be had from studying cells and different model organisms because of what we can learn on how the cells react and how organisms react. In addition to that, we have great hope for novel mechanism discovery and disease mechanism discovery, as well as 3D tissue engineering. In addition, as with all of your work, anything that leads to miniaturization and simplification, is also of great value for anything we do on Earth as well. Even after a number of decades of biological research in space, there's still a number of very important questions that remain unanswered. And the reason why they remain unanswered is because there are a number of very, very unique challenges, mostly relating to logistics into space. So our primary emphasis of research is actually looking at so-called primary human cells. These are cells of healthy organs, all of our organs, and we kind of go the entire span of any of those cells. And it is still unclear how most of these cells actually react when exposed to the space environment. We're also particularly interested in what happens inside the cell. This relates specifically to gene and protein expression, and how disease cells, such as cancer cells, for example, react differently. And you probably have heard this, that there have been studies before that showed that cancer cells are actually less aggressive, less malignant in cells. And what can we learn from that and translate to advanced science, but also potentially patient care in the future? I already alluded to this. There's still a number of very unique challenges. And one of the primary challenges I want to touch on is how to bring what we call healthy cells into space. And this does not relate to healthy tissue, because this also relates to cancer cells or other disease models. Because of the unique challenges of integration and length and growth time, we really need to discuss this and invent new methods to move forward. We are interested particularly in designing assays that run fully autonomously and on their own to only retrieve data, to really step away from the need to retrieve our payloads. And one of our unique challenges is to really provide a most adequate environment. We have very small margins that we can wiggle around in to not freeze or cook our cells. And finally, and this is one of the reasons why we're particularly interested in CubeSats, is that we are hoping to use CubeSat missions for higher reproducibility, more often launch or higher launch opportunities to really increase frequency and repeat experiments. To give you a broad overview on what we're interested in terms of our goals and aims, we're trying to expose a whole range of different cells to the space environment and then essentially observe through different methods how do these cells change, how does the morphology, meaning really just the appearance of the cell, change, what happens to the DNA. You're all probably very familiar with how DNA breaks essentially can cause cancer and different other diseases. What can we measure and how can we observe this in space and literally send the data back to evaluate and compare to our ground controls. I touched on this earlier, that one of the biggest challenges is actually to bring cells into space in a healthy environment, if you will. I want to go into this in a tiny bit of detail. When we normally study cells, most of our models do what we call proliferate. They multiply over a couple of days. And this is very helpful to us, but can be very challenging in space. What you see here in blue is kind of what happens at day one. The cells have attached to a plastic surface, which is intended, and they look really great. On day 2 and 3, they're really fantastic to study. This is where we want to run our assays, where we want to put our treatments on, etc. But then, if we don't tend to the cells and if we don't do anything to them, what happens, what you can see here in red, is significant overcrowding. And cells actually grow on top of each other. They lose interest in being metabolically active, and they die and change their behavior. And this has been shown again and again in different studies and is a huge issue for biological research in space and probably one of the most prohibitive reasons why most of the missions actually fail. This happens, in the time span of only 5 days, if you will, which means integration, travel to the point where you want to do your research is really, really limited. In order to combat this, we have developed a cellular hibernation protocol. And I want to show you a couple of pictures here, but there has been a slight problem between Mac and Windows. So I do apologize. You cannot see what day 1 looks like, but just trust me, it looks like the plate in blue. So there's a lot of space. The cells look very equal on both sides. And what we do is we put our hibernation solution on one of these plates and have our control cells just grow normally. We let these sit for 10 days, which is a humongously long amount of time. And what you can see here at the bottom on the left side, these cells are heavily overgrown. They're really crowded. So even if you've never looked at cells under the microscope before, these are really unhealthy. They're not happy. Well, in contrast, our cells that are hibernating, there's still room. There's plastic. They have room to grow. And we can quantify this by looking at cellular activity. And what you can see is that our hibernating cells are less active because we've reduced their metabolic activity for this entire time of 10 days. And by moving them out of that solution, we can then restore this. And now they're in our optimal conditions in that green window that you can see up top. To kind of go back to the whole CubeSat idea, we are interested in looking at different therapeutics that we want to test on our CubeSat. We have imaging and fluorescent imaging units. We can test organ chips or cells, and we're developing custom organ chips, analysis chips in our system as well. Our imaging system that we call MicroExplorer centers around a Sony imaging detector with a custom lens stack that allows us to image a number of different cell lines side by side on a microscope slide. So we can go 6 or 8 different cell lines or different treatments, or we could use an organ chip. And you can clearly see here that the system that is ultralight and very small in footprint and also runs on 5 volts is very capable for our needs. In addition, the imaging will provide us with a morphology summary, essentially. So we can look at how does the outline of the cell change, how do cell-cell interaction changes due to the space environment. And together with a collaborator, we are able to actually image inside the cell any occurring DNA damage due to the radiation exposure. As you can see in green here, these puncta at the bottom are essentially DNA strand breaks. I already mentioned protein detection. So I'm a protein person, actually. And so proteins, if you remember, is kind of what happens at the end of the road when gene expression is done. And when things have changed, so do proteins change. And so our aim is really to look at what does the cell secrete, so what does the cell spit out due to the change in the environment. And for that, we've developed a system that runs of what we call bioreactors. And you can see up here in these little chambers, there are the cells plated in there, and on top is about 2 mils of media, or the nutrients, and that contains proteins that the cells spat out. And we can move this onto a specialized membrane that has special antibodies to capture, and we can just image that. We stain this with a special dye, and a photo will tell us on orbit which one of these proteins is higher or lower than it was compared to our control. We're also interested in mitochondrial and metabolic function. You probably remember the mitochondria, the powerhouse of the cell. And here we're using another dye level where we can give the cells different nutrients that we know it can take up only when specific pathways inside the cell are still intact. And this, again, will tell us if on orbit something changes. If the cell can take up the dye or the nutrients, this dye changes significantly in color, while in comparison, if this pathway is now inhibited / the cell is damaged, the dye is no longer changed in color. So to summarize and to be mindful of my time, we're currently still developing like the overall concept for our biological payload. We're really hoping to create this as a fully autonomous payload to implement our hibernation and our different analysis chips, and to really only retrieve the data back at the end. We are having a number of different items that we make in-house, but we're also using the majority of the components are just off the shelf, which is obviously really helpful and leads to, budget-friendly development. And with that, I would like to thank everybody in the team I work with, and you for your time and attention, and be happy to take any questions. Thank you. So when you say healthy cells, you mean from astronauts? So I would always love to consider this, but unfortunately, even though, depending on which agency an astronaut is from, they are, often a little bit owned by the agency. In general, human research is very, very difficult. So we can't just go and do a biopsy. And even using, for example, blood, it's a very, very limited amount what you could get. So the challenges of retrieving that kind of tissue is very, very high to protect the astronauts. So unfortunately, it's not quite feasible. And any kind of, solid tissue, even skin, but, if we're talking liver, if we're talking, any other tissue, it's nearly impossible, unfortunately. Yeah, go ahead.
There are methods where you just put the cluster there, and then you can get the signature from that.
Yes, but I mean, this would be a single, like, so now we're talking like skin cells, skin fibroblasts, etc. So it would really limit the types of cells we could study, right? But overall, unfortunately, it's also very difficult to get any kind of tissue or, samples from the astronauts, even though it's a good thought. Yeah, so there were some more questions. Oh, up there, sorry. So technically, it actually would be very short because, as you maybe remember, a usual window of, healthy or good model system to overcrowding is easily within 5 days. So I think in total, depending on the cell type, you wouldn't look longer than 10 days for any of these experiments. The benefit of using the hibernation, as we're planning to do it, is that we could have different hibernating states on the CubeSat and kind of wake them up at different moments, and we could even make changes, talk to the system, make changes in terms of treatments, in terms of length, etc. So we're hoping to kind of iterate, which probably, increases the size of the CubeSat, but, that's kind of the dream to change that. Yeah. It's my understanding that that's probably necessary these days, yeah. So, but again, like our hope is, to actually partner with engineers. So I'm obviously more from the biology background, on all those systems in terms of avionics, et cetera. And we are essentially, focused on the payload on the biology side. Yeah. It's actually incredibly important. So one of the, and I didn't have time, unfortunately, to share this, but one of the main emphases of our program is actually to work on potential radiation protective drugs. This includes a number of different approaches, and it's not just necessarily a pill. There are different other more, natural products that could be helpful there. But essentially, the radiation is of the highest interest because as soon as we move outside of the Van Allen belt, that's our biggest challenge, right? We know now how the body reacts to microgravity as a whole, but what's really challenging and what will be challenging for long-term deep space missions is what can we do to protect organisms from radiation. It's everything and more. So it is definitely, this is true, right? It is absolutely the combination that, is going to be a real key to this. But the other thing is, and I apologize, I know that there's plenty more people in the audience that can answer the radiation question better than I do, but it's my understanding that mimicking galactic cosmic radiation on Earth is still very challenging. And it's very challenging to have the wide assortment of ions. Exactly, the mix and also kind of the repeatability and, interestingly enough, the low grade, right? We have a very low dose of high-powered ions, and all of that it's very difficult to mimic, even though I know that there are some excellent facilities here, yeah. Yeah, yeah. Last. It's a good question. I think for most tissues that is not the case. For complex systems, absolutely. So this is certainly something that you can see in fish and in worms, etc., that have been studied. For our cells, it's usually not a thing. I will say, though, that surprisingly, we sometimes see a summer-winter difference, weirdly enough, in the lab, which you think like, well, it's all, AC, but somehow that's still a thing. It's always good to keep these things in the back of your head, though, because you never really know, and we often assume a lot, and that's never a good idea. So, yeah. Thank you. I appreciate it. Sorry.
Thank you. Thank you so much, Chris Maynor. That was a great talk. Next up, we've got Alex Mason from Bright Ascension. So please welcome Alex Mason.
Okay, good morning everyone. My name's Alex Mason. I'm a software developer at Bright Ascension. And over the years, we've had quite a lot of experience, both good and bad, with payload interfacing. So today I'd quite like to give you a little insight into some of our experiences and some lessons learned. First of all, a bit of background information on Bright Ascension and what we do. So we are a space software company based out of Scotland, and we do off-the-shelf software products. We do a flight software development kit and mission control software, and we also do software services. We've been going since about 2014, and today we have 33 spacecraft flying using our software. We've got many more in development. Our software is used for a wide range of applications, from commercial comms, university CubeSat demonstration programs, and Earth observation. And we are having customers all over the world, and we collaborate with commercial and non-commercial partners on research and development projects. Okay, so mission payloads. We find that payloads for a mission tend to be the driving force behind the timeline for the missions that we've been working on. So they are often defined, often the payloads and the platform are being designed and developed at the same time. And while the payload teams are experts in what they do, and they're really good at building payloads, they're not necessarily space experts or experts in operating spacecraft. And often it's expected that they're supposed to design the interface to their payload themselves. We've found, in our experience, this has led to some very arbitrary design choices, and we frequently have to make changes late in development. Having multiple payloads on a mission tends to amplify these problems. And this was certainly the case on our first mission, UCube-1. So back in 2014, we had the privilege of writing the flight software and the ground software for the UK Space Agency's first CubeSat mission. So this was 3U CubeSat, the platform provided by CloudSpace, and it had 6 payloads crammed into it. And each of these payloads was developed by an independent partner organization. They were all very different from each other, and there was a very ambitious timescale for getting the project finished. So in order to mitigate the risk of issues cropping up during integration, the satellite integrator provided a payload protocol which all the payload teams were supposed to follow, so that they would all be able to work with the payloads in the same way. Unfortunately, all of the payloads interpreted this protocol in a very, very different fashion. So some of the payloads, although they were all based on the same platform at the bits and bytes layer, people did not pay attention to what the protocol actually meant. And we also didn't get around to being able to test the payload integration until very late in development. And once we got those together, we found significant issues. So we found that, despite having a well-defined payload protocol interface, there's a lot more to having a successful mission than just the bits and bytes of the representation on the wire. So we had two different protocols used on board, one for each interface. And it's a good idea to have support for multiple interfaces if you can do it, because it allows you to be much more flexible. But in our experience, we've now learned that it's better to have a single high-level protocol and map those information in that protocol to the representation on the wire and the individual interfaces. So, for example, don't have a multiple protocol, one for each of CAN, SPI, I2C. Have a single high-level protocol and map, for example, parameter accesses, read and writes to bus read and writes. And one of the benefits of doing things that way is that you can reuse software which has been written to drive a particular payload, even if you change the underlying interfaces later in development. Another thing to keep in mind is choosing your interfaces very carefully based on how reliable they're going to be. So over the years, we've encountered numerous problems with spacecraft payloads using I2C because it has some very strange failure modes, which have been very difficult to debug on orbit. We've also found a source of defects to be very complex state machines, which can arise from the asynchronous nature of serial interfaces. So the big problem that we found on UCube was that having this sort of on-the-wire protocol compliance did not mean that all the payloads played nicely with the platform or with each other. So the most significant problems that we try to address are in terms of semantics. So semantics is what the various protocol units actually mean and how they're intended to be used. So over the years, we've defined a core set of payload semantics, core set of services. And these services form the bridge between your high-level ConOps and the sort of low-level representation on the wire. So we have settled on these services, which we found have covered about 80 to 90% of the needs of most payloads that we've encountered. So we do things like being able to do basic telecommanding, being able to do access to structured data, being able to access parameter values, being able to access uplink and downlink files, and being able to uplink new software images. And all of our services have a minimal implementation set. And the idea behind that is to make people more inclined to be compliant to them. So we mark much of the services operations as optional. So people need to implement them if they need to. We found that the best place to start when thinking about payload interfacing is with the concept of operation. So long before you think about payload protocols or what interfaces to choose to use. So we found that on many missions there's been a big mismatch between how the payload developers and the operators think that the payloads are going to be operated. And often this leads to problems that can be fixed in software, late into development. But it's obviously that fixing things late in development adds complexity, adds risk, and adds cost. So it's better to have a well thought out and sort of really well understood and agreed concept of operations before you begin thinking about protocol. So the way that we approach this is we have a sort of standard development lifecycle, where we capture sort of information about the entire mission and the payloads in a model. And capturing this information lets us do all sorts of things. So we can, for example, use that captured information to configure test environments. So if we have information about all of the parameters and actions that a particular payload is exposing, we can give the payload developer a platform emulator. So a piece of software that pretends to be the platform from the perspective of the payload. And this lets the payload be integrated with a version of the spacecraft very early in development. And these emulators can run on cheap commodity hardware like Raspberry Pis or a BeagleBone. So what is a model? The model is just a structured collection of data about your mission and your payload. It's a single source of truth that you can share amongst members of the team to communicate with the rest of them about what's in your payload, how do you interact with it. And it also captures things like documentation for both operators and developers. Back on UCube, the first version of this was implemented in a spreadsheet. And we found that spreadsheets are a pretty good place to start. So if you're starting from scratch with this, spreadsheets are a good way to do it. The data in spreadsheet is structured. And you can read a spreadsheet anywhere, and data inside them can be ingested into tools to help with test and development, sort of very easily. Nowadays, we use a much more advanced set of toolings that work with a richer set of data, which is defined in a meta model. So a meta model is basically just information about a model itself. So what parts are you allowed to build a model from? So the sorts of things we have in there, we can express services themselves and how they're set up. So like what operations they have and what protocol semantics that they talk, like maybe it's probably talk master-slave, maybe talk peer-to-peer. We also have sort of all the documentation for the spacecraft, and we have high-level operations. So all of the like procedure execution for all the operations to interact with your payload. What we don't have in the model is a definition of the on-the-wire encoding and data transfers. So instead, we rely on having a type system and our defined semantic services along with the canonical encoding. So this approach will be familiar to those of you who've used things like Google's protobufs and gRPC or Apache Thrift. So if you're not using our tools on a mission, then these will be technologies that you should go and check out. So where have we put this into practice? So we've used our model-based approach to payload integration on a hosted payload mission called Faraday. So Faraday Phoenix is a 6U CubeSat developed by in-space missions, and it has a large number of payloads on board, some of which are software defined. And all of these payloads used our model. We found that, particularly compared to UCube, we had very few issues with test and integration of payloads into the system. We've also been working with the UK's Satellite Applications Catapult in-orbit demonstrator missions for a number of years. So the in-orbit demonstrator program is a program designed to make it easier to demonstrate novel payloads and space-based services. So it's based on an AAC CLIDE-based platform, and the most recent IOD mission is called Amber, and it's for Horizon Technologies. So we gave Horizon a system emulator, which they were able to use to test integration of their payload into the platform long before the platform was ready. So for every mission we get involved with, we pick up some experience, and we take that experience, we put it back into our tools. So around 10 payloads have used our standard model-based approach to payload interfacing so far, and we found that we have much improved the way that we work compared to when we did with UCube. So we have very few issues with integration and test. We're currently expanding the expression of our model, so increasing the number of things that can be represented in our model, and all of these tools that work with the model can be found in our flight software development kit, which is available free of charge to universities through our academic program. So to sum up, operations-led approach to payload interfacing leads to significant time savings and reduced risk. We found that the most effective thing that you can do to improve payload interfacing is to capture all the information about the mission and your payloads in a model. So you have a single source of truth that make it machine readable so that you can generate software to test your payloads early in your mission. Two questions? Okay. So if anyone's got any questions, then I'd be pleased to take them now. Otherwise, I do have a booth upstairs, so you can come and chat to me. Sure.
Do you have a security framework for your model, for your approach?
We don't have a security framework as such, but the way that we layer our comm stacks is we can have, like, for example, at the data link layer, we'll use CCSDS-based data link security. But there's no sort of security development life cycle in our model. At the back. Yes, absolutely. So the question there was, do third parties, would we be willing to let them write software using our tools? And the answer is yes, for sure. Okay, I think that's all I have time for. Thanks for your attention, and enjoy the rest of the conference. Thanks, man.
All right, thank you so much, Alex Mason. Those were some pretty cool slides. So next up, we have Danny Coogan from the Precision Space Systems Laboratory at the University of Florida. Please welcome Danny Coogan.
Hello, everyone. I'm Danny Coogan again. I'm at the University of Florida's Precision Space Systems Lab, and today I'll be talking about my simulation work on the estimation of timing performance with pulsed laser links for small satellite positioning, navigation, and timing, which is a lot of words, but I'll go into the details. So I'm going to discuss some of the context for this work and then the actual simulation, which includes a clock noise simulation, as well as a clock model estimation of that clock noise, and then I'll conclude. So for those who aren't familiar, why time transfer? So one of the reasons that time transfer is performed is for synchronizing clocks, because clocks are imperfect. And in applications for relativistic physics, for example, in deep space, this can be important for synchronizing clocks. And some other applications are navigation and RF interferometry. And so currently, radio frequency is common for doing time transfer, but research and industry is going towards using optics, so lasers, for performing this, as well as laser communication. So what is the clock offset? On the very basic level, if you have two different clocks, you want to know at a single instant what is the difference between those two clocks, so a T2 minus a T1. To go more into detail of how you would measure time transfer, if you had two spacecraft, like in that diagram there, you have spacecraft 1 will transmit a laser pulse to spacecraft 2 at time T1 according to its clock. Then that pulse will travel and be received at spacecraft 2 at time T2 according to spacecraft 2's clock. And the difference between those two times, and as well as the light travel time tau, is going to be your clock offset in a one-way time transfer method. Okay, so in this simulation, I simulated measurements, which measurements have noise, as well as the actual clock offsets between the two separate spacecraft are a type of non-stationary time series. And so the CSAC and MAC are the two time series of clock offsets that I created that I'll discuss between the two different spacecraft. And then I also simulated a GPS timing measurement as a source of noise for GPS timing measurements. So the other noise sources I included are a Gaussian-based pulse detection noise from the electronics, as well as a GPS position error. And below, I've cited some of the sources of where I'm getting these numbers from. And so the first goal of creating the time series was to create a time series that as closely matched the Allen deviation as my references that I was basing them off of. And so here are some of the results. So I developed 3 different sets. And so this is just for comparison. I show here one of the sets of time series of those clock offsets. So I have a MAC, a CSAC, and then that GPS noise time series all together there. And then here is the Allen deviations of those time series. And so the Allen deviation is used as a way to compare different clocks. It is a quantified way to show the different frequency stabilities over different averaging times of these clocks. And so here I'm just showing a comparison of the Allen deviations of the time series I just showed in comparison to their references, as well as some chomped on-orbit data. And so chomped is one of the University of Florida's missions, and we use the CSAC, so that's there as well. And so the mission concept of the simulation in which these time series were used, I took some of those simulation parameters and based them off of the T2L2 mission, chomped and click parameters. And so I have these 2 spacecraft in low Earth orbit, and they're performing laser time transfer with each other at spacecraft to spacecraft. Okay. And this is just a visualization of what the simulation is showing. So spacecraft 1 sends a laser pulse at time t, which is received at time t plus that light travel time tau by spacecraft 2. And so we'll go into the details of how to measure that. And so here, again, this is kind of a still frame of the animation I just showed. So you can see that the spacecraft 1 sends that laser pulse at time t, again received at spacecraft 2 at time t plus tau. And then we want to know the clock offset and as well measure the light travel time. And so tau is the light travel time, which I used as a measurement in the form of distance, so just multiplying it by the speed of light. And that had to be solved iteratively. So this is the way I simulated laser pulse light travel time measurements, which I then use here, which is in an estimation filter. So I developed an orbital estimation filter, which uses the orbital dynamics and the GPS data measurements I simulated, as well as the measured light travel time from the lasing simulation. And I set this problem up as a non-linear least squares problem, which was then solved using the Gauss-Newton method, which is iterative. And the outcome of that was initial position velocity of both spacecraft and constant clock coefficients, which I'll discuss a little detail. So the goal of this was to estimate the true clock offset, so those time series that I showed earlier of the CSAC and the MAC, that's the true clock offset between the independent clocks on the spacecraft. And so we use this filter to really of interest is the clock coefficients, which are constant. And these are used, this is an example of a quadratic because I was using a polynomial model to fit to that time series. So I would have 3 constant clock coefficients that I'm interested in finding. And so here are some of the results. Overall, lasing reduced the RMS error by about 80% on average. I did 3 different independent sets, so that's where my average is coming from. And here in the plot, I'm showing a, this is for a 8th order polynomial, a MAC from my first set of time series. And so you can see that using only GPS measurements for the estimation, I get that kind of orange line. And if I include the lasing measurements in that estimation, I get a much closer fit to the true clock offset. And then I have just some example values of those results. And here again, I have those same lines, but now I'm comparing them to a fit to the true clock offset time series. So the others were created using the measurements and the estimation filter, and you can see that including the lasing measurements in that estimation filter gives a much closer fit to the what would be the optimal fit, which is just fitting directly to the true time series. And here I'm comparing the CSAC and MAC across the different types of polynomials I looked at. So I looked at quadratic through ninth order. And overall, using a higher order polynomial improves the model. And just to wrap up and conclude, the purpose of the simulation and what it would be of interest to be used in is for mission development and analysis and estimating timing performance for those missions. Again, I was simulating 2 spacecraft in low Earth orbit, exchanging laser pulses and receiving GPS and timing measurements in addition to that. And these results showed that overall lasing measurements greatly improved reduced the RMS error, and increasing the polynomial order overall on average increased the quality of the fit. And I'd like to thank everyone who supported this work. If there are any questions, I'll take them now. Okay. Yes.
What are you assuming the aperture looks like for the receiver, for the optical pulse?
So I did not really go into the hardware for this. So yeah, that was just kind of, yes, exactly. Anybody else? I'll also be around later if anyone wants to come find me to discuss. I also have a poster upstairs, so I'll be around that if you have more questions or want to look at this in poster form. If there aren't any more questions, thank you.
All right, thank you so much, Danny Coogan. So next up, we've got Václav Lazar from the Brno University of Technology. Please welcome Václav Lazar.
Hello. Thank you for having me here today. So I'm the guy dealing you from your lunch. So I'm going to be quick, I hope. The BATCube, the name comes from Brno University of Technology, the university we are the project having on. So basically we are 5 guys, 5 team members without no previous CubeSat experience or whatsoever. We got it in order to apply for a university grant that we were awarded last year. So we defined some of the CubeSat project objectives that we have. The main objective we have is the 1U CubeSat development unit, which is kind of challenging because we are starting from scratch because of the previous experience. And also we have some of the secondary objectives. We plan to adapt the technology demonstration within our academic conditions. And, for example, to establish a student platform, since this is the very first CubeSat project at our university. And these are some of the highlights of our project, as we have the project right now. We are really proud that we have the first CubeSat project at our university, and also we incorporate, for example, the ESA flare satellite design specification. I will get onto it later on as well. So as for the mission, we had a mission proposal for solar eclipse observation for the solar corona research purposes. The observation is to be done in a visible wavelength, also known as a white light observations. And unlike the coronagraphs that you might know, we plan to use a moon as a cooler for the solar disk during the observations. In that way, we can get some really unique data of the close solar surface region that remains blind in coronagraph observations. And for that, we had to put together some of the various observation conditions, and so we defined some of the orbit searching algorithm, and we get some of the results of the potential observation orbits. Now, there are two kinds of the results we get. These are the unique observation opportunities and also the concurrent observation opportunities. While the unique observation means that there is no Earth observation counterpart to it, and the concurrent means that, for example, if the total solar eclipse event happens on the ground, then we can observe the very same event from the ground and also from the space. Yeah, so it pretty much summarizes these pictures, because in, for example, 25, we will have a partial eclipse event on the ground in a Greenland and Canada region, and such an observation cannot be done from Earth. And with our mission, we could be, we could, for example, utilize the specialized orbit to get a total solar eclipse observation images from this year. In 2026, there is also on-ground and also spaceborne observation opportunity. Yeah, back to the hardware. So we start with a plastic fast prototyping 3D printing, but we hope that the final product of our demonstration mission will be printed from the peak material, which is thermoplastic, also known as ULTEM, as you might know. For now, we stick with a 6 pieces construction that is mounted together with some screws and nuts. As for the hardware, we apply the flyer satellite design specification mentioned earlier. This is something parallel to your NASA CubeSat Launch Initiative program. And we put together the demonstration mission requirements in order to design hardware as well. And the demonstration mission is to take images on one new CubeSat and to process the images in the very same way as they would be processed during the flight mission, observing the solar corona later on. We stick with the usual interfaces as for RS, QSPI, and CAN. We got 3 independent power lines on the APS bus and usual stuff there. And I want to conclude my presentation with our display of the in-house made solar panels. And to my knowledge, they work, so it should be like very good news and happy ending of my presentation, because I'm kind of proud we didn't know anything about the CubeSats. Now we are presenting here. So yeah, as Carl Sagan would say in Cosmos in 1980, if you want to make an apple pie from scratch, you must first invent the universe. And I see a nice parallel to it, because all the things you are doing here, you guys, you are all making a small universes, and I think it is nice. So yeah, thank you for your attention. If you have any questions, like, shut them up. Yes. Okay, we implement the manufacturing, the 3D printing for the structure. Yeah. Yeah, the main frame is 3D printed. The boards are normal stacked PCBs, conventionally made. Okay, thanks a lot. Enjoy your lunch. Okay, one more question. I'm not a hardware guy. If you know down the name of the component, you can download the datasheet. These are normally available off-shelf components. Okay, thank you.
All right, thank you very much, Václav. So that is the last presentation. We're going to have a lunch break. We'd like to thank Blue Canyon Technologies, UARX, and Millennium Space Systems for providing the lunch and all of the beverages. So I hope you have a good lunch, and we'll be starting back up at 1:15.
Hey, good afternoon, everybody. Hopefully everyone had a good, delicious lunch. I would like to thank UARCS again for sponsoring that. And we have a quick sponsor video with them. And next up, I'd also like to present Mateo from D-Orbit to present his presentation. Thank you.
Introducing WAR Space Launch Services. TOM is our solution to carry our customers to the launcher's drop-off orbit. Aussie is our OTV. It uses chemical propulsion, which is ideal for those customers who need a fast ride to specific locations. Rami, our CubeSat deployer, provides extra space for your satellite. It was designed for interplanetary missions, providing optional extra services on LEO missions. Sauron, our family of separation systems, allows us to accommodate small satellites that don't follow the CubeSat standard. We have developed the most advanced separation systems available on the market. With them, we provide launch services and in-space logistics to cover our customer needs. We are WARS. We are your ride in space.
Hello, everybody. Well, it's quite hard to talk after WARS, as I'm going to talk about more or less about the same thing. I'm Matteo. I'm sorry you were expecting for Eleonora, who is a very nice blonde, but you have me, so I hope it's gonna work anyway. But let's start. So I'm Matteo. I'm launch strategy manager in the Orbit. The Orbit is a space transportation company that has been founded in 2011 and has its headquarters in Finomore Nasco, close to the Como Lake. Quite nice spot. Then we also have other 3 subsidiaries. One is in Lisbon, Portugal, which is our software house. Then we also have another subsidiary in UK, close to London, and then a commercial subsidiary in Washington, DC. We are more or less in total almost 200 people, and we are growing. And the target that we are having today is to become one of the main space transportation companies. So what we do is delivering the last mile for constellation or for single satellites that are released by rideshare launcher. In our future, we are targeting instead to be like a real in-orbit servicing company. So far, we reached a couple of very interesting targets. The first one is that we have been the first company in the world to provide a commercial service in terms of last mile delivery. And we are also the first company that has been able to provide satellite as a service through our IoT services. Okay, let's go and see a bit more about products and services. As I was mentioning before, we can do everything through our ION platform. Our ION platform has been thinking in order to provide launch services. Launch services means that we can take everything from Earth to space, and we can go through this platform that is able to release single satellite to any orbit, even to the drop-off orbit of the launcher, or then provide maneuver so that we can reach a specific orbit that can implement and can increase the target, that can make the target of the mission much more useful for the end user. Once the mission is done, the deployment phase is done, we start with our IoD service. IoD service means that we can have on board hosted payload that wants to test their technology without having the need of building a full satellite. That therefore allows to save some money. As I was mentioning before, in the future we are targeting to start providing in-orbit services that will take an advantage of robotics and the technology that is improving so that we can start using rendezvous in orbit so that we can start recycling and keep the space clean, which is more or less what we want to do if you think that the name of the company is actually the Orbit. Yeah, this is a bit introduction on Ion itself. Ion is our carrier, which, thanks to its own propulsion, is able to move around in space. The mission works like that. Our customers bring their satellite in our facilities in Italy. We integrate them inside our Ion. Then we ship Ion to the launch base. That can be in French Guiana, or when launching with Vega, or in Cape Canaveral, when launching with SpaceX. And then we start a mission. Once the launcher drop us off and we are in space, we then deploy satellites that we have on board, and then we start maneuvers in order to bring our customers to their exact orbit. But which kind of maneuvers we can do? So in order to make it clearer, I would like to use a quick example. In this case, we can provide 3 maneuvers. The first one is orbit raising. The orbit raising is basically what we do in order to bring a CubeSat from a point A to a point B, which has an higher altitude. So, for instance, we have a satellite that is being dropped off at 500 kilometers, but then for some reason in their mission, they need to get to 650 kilometers. How they can do? They embark with Ion. We perform a maneuver and then a counter maneuver in order to increase and then circularize the apogee, and we deploy the satellite so that the satellite can operate in its final altitude. Then we also can perform true anomaly phasing, which is perfect for constellations, because when you're dropped off from the single launcher, you're in a kind of cluster, but then it would be very useful if somebody could split them around the orbit, and this is exactly what we do. We start we start changing slightly the inclination, and then we go back to the right inclination to deploy the satellite, and this allows us to have the constellation fully deployed, and we can save the time of spacing up to 85% with respect to a differential drag or a cluster release. Last thing that is being quite revolutionary in this sector is the run shift maneuver, which takes advantage of the J2 effect in order to torque and change the ascending node of the satellites that we want to release. Just to give an applicative example, think about a constellation of 8 satellites, 8 6Us maybe, that can be onboarded on Ion. We release the first 4 through the anomaly, with the true anomaly phasing in the first orbit. Then we start our maneuver, our run shift maneuver, and then we can start the second part of the constellation in a new orbit, allowing the customers to have the constellation fully deployed with only one launch on 2 different orbital planes. As I was mentioning before, once all of this part of the mission related to the deployment is over, we start our hosted payload mission that is very helpful for all the research entities that want to test technology without the need of building a real satellite. This is quite useful because allow to this center to save money and save time, and therefore increase the research. And this is something that we were very proud, because in our last missions we have been able to really accelerate many projects, and we are very proud of it. So as I just said, past missions. Let's see which is our heritage. We in total have done so far 5 missions. The next one will be end of May, beginning of June, with SpaceX, but let's start from the beginning. Our first mission has been in 2020 with the Vega. We launched our Ion Mark 1, and for the first time we validate in orbit our software, which is Aurora, that I forgot to mention before when talking about products, which is the software that we use to control all the satellites that we deployed in orbit. And the first mission has been very helpful in order to test and validate this software. Our second mission instead has been very, very important, because for the first time we tested the hosted payload services, and we launched with SpaceX in January 2021. Third and fourth mission have been quite helpful, because we have been able to test in orbit our cloud system. So what we are doing is, as you can think, every time that we deploy an Ion in orbit, we have a real satellite in orbit, so we don't want to waste resources. So once the phase for our customers are done and are over, we start using our satellite in order to give something and to improve our internal experiment. And we are now testing edge computing, and both the third and the fourth mission have been very helpful reaching this target. Our last mission, instead, has been launched in April, always with SpaceX. I cannot tell you, unfortunately, what we are testing, because until we don't do things, we cannot say things, because it's like bad luck. But we will keep posted about it. And we had on board, which is nice to mention, Chilean satellites. And for the first time, we launched 3 satellites for Chile. And this was a great achievement also for the country. Okay. Now I'm finishing. Just a couple of examples of what we can do with Ion. This is an example of what we've done in our Ion Mark I. We had on board the 12 planets satellite. You can see on the right the standard deployment. So they launched with Vega and they've been released in a cluster. This instead is the example of the 12 satellites that were onboarded on Ion. You can see that with the standard deployment, after 2 months, the satellites were more or less still together, while you can see that after 2 months, with the fast dispersion that we performed through Ion, the satellites are quite well spaced around the orbit. Of course, those are just 1 month after the launch, waiting for more time. We would expected to have the full constellation fully deployed. And instead, I want to also say something about our IoT services. This is a nice example that I always like to mention when give presentation, because this is on our CV2, and the customer here was the Institute of Canary Islands, where they are very specialized in Earth observation. We tested their camera in the hosted payload services that we can provide. You can see the difference of the pictures here between Drago, which is the hosted payload that we had on board, and the Sentinel Copernicus here. But what is really weird, that I cannot say nice, that I don't know if you remember that a couple of years ago, there have been a volcano exploding in Canary Islands. And we had on board the Earth observation, the camera from Institute of Canary Islands. So we changed our mission, and we have been able to take pictures of the volcano, as you can see here. The image down there is what we have been able to achieve with post-processing of the picture. And this was actually the volcano erupting. It was quite nice, this mission, and quite helpful also for the Canary Islands as well. Now, I think that I'm time. I would like to thank you for the attention. And if it's going to work, I would like to show you a video of, as you can see, there is a satellite that has been just released by Ion. And this is the Earth, and that's it. If you have any question, I'm here. Thank you very much. Question? Can you repeat, please? Yes, we do. Actually, this depends on the full mission. So, as you can imagine, like the time is strictly related to the propellant that we have on board. So, how many customers will need to use that propellant, and how much will be the mass to move from one point to another point? Let's say that we assume that 1 hour every 1 month and a half, 2 months is a good assumption, but then mission by mission, we can review and tune this time. Any other question? Looks like no. Okay, perfect. Thank you very much, guys.
All right, well, thank you so much, Matteo. Now, please let's welcome Maggie from NanoRacks to the stage. Thank you.
Hello. My name is Maggie Ahern. I am a senior mission manager at NanoRacks. A lot of you, I'm assuming here, have worked with NanoRacks, and if you've worked with a mission manager, you know that we wear a lot of hats. And since starting within the organization, I've had the opportunity to work with our CubeSat program. I now lead our hosted payloads program, and I've also been able to work with our advanced concepts program. And kind of leveraging all of that different information and experiences, I've had this ability to kind of look at where we can start leveraging hosted platforms as risk mitigation missions for CubeSat and small sat development projects. So we'll kind of start just looking at prototyping concepts and just a generic architecture that we can use to evaluate hosted platforms for this use case for risk reduction missions. So ultimately, in developing advanced technologies, this requires, this really delicate balance between technical feasibility and technical demonstration. If it's not feasible, you can't demonstrate it. And so it's really the cyclical process, as you guys are aware of. You have a technology need, then you start developing your prototype, you test it, you diagnose it, and you're characterizing behaviors, because maybe you don't have such rigid requirements because you need to reduce that developmental timeline to develop that prototype. And then you respond, and that's a really iterative process, as you guys all know, and with the intention of building a proto flight, something that we can fly. So that leads me into introducing hosted platforms. I'm going to be focusing primarily on ISS hosted platforms. There's so many options out there for that, and there's also obviously hosting on satellite missions as well. I'm going to focus on ISS because there is that great opportunity of returning your payload after the mission to investigate maybe where things went wrong, where you can build a more robust systems and things like that. So as an overview, I'm going to use the NanoRacks external platform as an example, but again, there's so many out there to lean upon. So hosted platforms are such a critical piece of infrastructure because they provide power and data for payloads. They also allow for servicing of real-time operations and troubleshooting, as well as the ability to return the hardware, which I mentioned. So on the left here, you can see our hosted payload platform. What's cool about this platform is there's a passive and a powered side. We can leverage modified base plates to use the upper volume if we need kind of non-standard form factors. But typically, the top is used for biologicals or material science, which is great, especially, if you're 3D printing interesting composite materials. That's a really great use case for those positive, the passive side, which is 6 through 9. And then below, we have 1 through 5, and these are our powered slots. So you receive 28-volt power, and then you also have data, real-time operations, and a lot of times we really lean upon that CubeSat form factor such that you can translate missions from that hosted payload application to CubeSat or small sat form factors. In the middle, you can see a crew member installing a hosted payload. What's so great about this is our payloads are launched in pressurized cargo, so it's a really soft ride. You're launched in a custom, basically foam clamshell and wrapped in bubble wrap. So from a vibrational perspective, it's really low impact. And what's also great is the crew members can inspect your payload. So for example, if you're an imager, they can inspect if there's any fractured components, whether in the actual housing or in the window or anything internal to the structure. From there, it goes through the GEM airlock, and then it's grappled and put on our external facility on the ISS. Once installed on the ISS, there are so many capabilities open to you at that point. Obviously, before even getting installed, you get a ton of information and data on the thermal environments, as well as anything in your field of view, especially if you're an imager. What is your visibility? Are there any payloads that are adjacent to you that may impact your mission? So you get a lot of data with that as well. And then once you're installed, you have access to 1 Hertz telemetry from the ISS, so you can real-time respond to the environments that you're experiencing on your payload platform, and then you can respond to that real-time, which is great. And so there are so many types of technologies that we utilize, obviously, for CubeSats and small sats. So what I did was I looked at over 100 CubeSats and I categorized the primary technologies that we're seeing being tested. I may not have covered them all, but these seem to be the primary ones. And then I categorized them into what I believe is really well suited for hosted payload platforms, and then what's probably better suited for CubeSats. So as mentioned, the bread and butter of hosted payloads is sensors and imagers. Any sort of detection, events, CPUs, and deployables, I should caveat, if it's an antenna, a solar array, I think those are great options. If you have a tether with a balloon on it, NASA safety is going to freak out. So I would say definitely caveat the deployables, but for materials, as mentioned on the passive side of the NREP platform, that's a great option to look to see how your structures respond in that radiation environment. And also communications. And I think communications is something really interesting because sometimes if it hasn't been tested historically on the ISS, we're a little afraid of it. But we can do a lot of feasibility studies and all sorts of analyses to evaluate whether or not certain communication applications are viable for hosted platforms. And then kind of as I mentioned, tethers are a no-go. High radio frequency radios is just dependent on how high frequency, and we'll kind of do an EMI analysis to evaluate whether or not that's viable. Lasers, solar sails, and then obviously kind of everything from there, capsules, propulsion, formation flying. Those are instances where there's just no feasibility there as well for the mission because those require you to be a free flyer. So kind of going into it, I categorized basically 4 different types of prototyping strategies and really based in schedule and budget and how those impact scale, scope, capability. So here we have small budget, a tight schedule. I really view this as an organization that's just emerging into the space industry. They're getting started. They received a small amount of seed funding to develop some sort of capability and advanced concept. So they really need to meet that next milestone as quickly as possible. So there's major impacts to the scale, scope, and capability just due to the fact that you're working on a small budget. And because you're on a tight schedule, there's a limited integration, launch, and deployment opportunity, so you really have to play with when can you be launched, when you can be deployed or hosted. So that's a critical consideration as well. And as mentioned on the first slide, with kind of that generic prototyping architecture, it's important to have those flexible requirements such that you're meeting your primary mission objectives, but you're able to adapt as you're building the system to rapidly develop it. The second one, so small budget and a long schedule. I view this as most CubeSat projects, right? You guys get funding through your educational organization or maybe some other subsidiary funding. And you have a long schedule that maybe covers the entire duration of, maybe a cohort of students or, multiple years of students. So this, I think most of everyone here probably falls within this category. If you don't and you do have a large budget, that's incredible, and kudos to you. But, working with this, really here, it's, the small budget plays into what's the labor cost and what's the potential for subsidiary funding. Conveniently, with students, I don't want to call it free labor, but that is part of it, and that plays into the cost out of these types of missions and why it is so viable with a small budget, but leaning on that long schedule. As well as developing your capability. There's numerous integration, launch, and deployment opportunities, which is really great because if the capability isn't there, you don't have to rush it, that you can slip to later flights. And then the kind of last one I'll really focus on is the large budget and the tight schedule. Now, this one is great if you have those components available to you. And I think with COVID over the last 2 years, we saw a huge impact to component availability, and that's something that we can't control. So whether or not you have availability to expert knowledge or that component, that can play a huge role into the success of your mission. And as well, since you're dealing with that tight schedule, you have limited integration, launch and deployment opportunities, so you have to time that up as effectively as possible. And then the last one, I'll briefly touch on it, a large budget, a long schedule. You're in the best case scenario, and you probably aren't sitting in this room because you're living our best lives. So the 2 different strategies I have kind of highlighted in red here, this is really the 2 scenarios where I view hosted platforms to play that critical role, specifically due to the tight schedule. And it's about getting your payload capability, advanced technology to space as quick as possible. So it's kind of this race for flight heritage, especially with hosted platforms. There's kind of this future where you only need to fly the component. You don't need to build out all of the subsystems. So you're dramatically reducing the amount of development time to build out your system, but you're still achieving that flight heritage as quickly as possible. So if you break it down, your system to just a component level, a novel technology, reaching that TRL 5, if your system allows for flying on the hosted payload or the hosted platform as an entire system, reaching that TRL 6, but that's really where I think hosted payloads offer the most benefit to CubeSat developers, is in obtaining this flight heritage, gaining additional funding, and then being able to develop, larger, whether it be CubeSat constellations, small sats, or even larger satellites. So kind of a breakdown of development timeline, and there's so many caveats with this one, but for a hosted mission, from that contract execution to installation, we can make about 9 months, and I think that really comes down to your average payload. So if we have an imager, it's not high voltage, there's nothing, deploying off of it, that's something that we can rapidly get on orbit and installed. As opposed to CubeSats, which generally take about 2 years, and I think the caveat there is where you are when you come to a servicer or an integrator. If you're at a PDR level versus a CDR level, if you're ready to go, maybe we can also get you there in 6 months. But so on average, looking at 2 years, but definitely a lot of caveats there depending on where you are in that development cycle. So developmental challenges, and I think this is something that we've always experienced, but it come to light in the last 2 years. Those subsystem components that you're developing to build out the entire system beyond your advanced concept or technology was impacted by COVID or any sort of pandemic that we may experience in the future or have experienced in the past. Also, any sort of natural disasters that impacts the infrastructure that provides us these critical components for our subsystems. And unfortunately, kind of a quick economic lesson, if you have maintained or sustained demand for a component or some sort of COTS, material, and there's a reduced availability of it, that cost is going to go up, and obviously that's a programmatic risk to you and your mission. So really what the recommendation is, consider just flying those components, those critical unproven components, those advanced technologies that really need the flight heritage while you slowly build out those subsystems for future missions. So form factors, I think, is a really interesting conversation between CubeSats and hosted platforms. We really lean on that heritage of the CubeSat form factor because it is so standardized and it has reduced that barrier to entry. Now looking at hosted payload platforms, you can see we have leveraged that 1U, 2U, 3U. But what's great is when you don't fit in that really fine constraint of the rails or the tabs or whatever you're using, and you need a couple more millimeters, and that would increase the capability of your technology, you have that with the hosted platform, whether we have an adapted base plate and you can do more of an L shape, or if you just need a couple more millimeters or centimeters here and there. This is really where hosted platforms become more configurable and really well suited for small sat missions because you don't need to fit in that fine CubeSat form factor. You can allocate additional swap. So there's a lot of key advantages there as well. So spacecraft expenditures, I kind of picked out the primary expenditure types that you'll see in looking at the projects we brought through our organization, but also industry-wide. It looks at about 77% of the overall cost of whether a small sat or a CubeSat is on the spacecraft bus. So I think this is a really interesting kind of concept from also a cost side, but also from a swap side, the fact that as you develop your payload, you're actually having to allocate so many resources to developing that bus that you have to reduce your swap allocation to the actual science that you're developing. So on the hosted payload side, you obviously benefit from not having to allocate so many resources to actually building, subsidiary systems, and really leverage the fact that you can increase your wattage, you can increase your size, and you can increase your weight and your power, and then leverage non-standard form factors to create the best capability you can for whatever it is that you're studying or researching. And the launch is also a really interesting kind of concept because with CubeSats, a lot of times, as you guys know, and if you saw our deployer upstairs, a lot of times you're coupled with other programs. So there might be multiple CubeSats in your launcher, and if they're delayed, your integration can be delayed. With hosted payloads, you're an independent mission. You fly on your own. We don't integrate you onto the platform until you are on orbit, and a crew member does that for us. So that's a really great opportunity to be independent. You control that risk. And so when you're ready, you can launch, and we will install you. From a program cost perspective, CubeSats require a little bit more environmental testing, and that's not always the case, but as we bring hosted payloads through that NASA safety process, they have discretion over what environmental tests that we have to perform on our hosted payloads. So sometimes we don't have to perform vibrational testing, for example. Please always perform vibrational testing. But, obviously that's critically important, but you don't necessarily have to meet the same standards. As mentioned before, you're launched in bubble wrap, you're in pressurized cargo, and you're in a custom foam clamshells, so it's a really soft ride up. So you can test to what you believe is the right limit, but you don't necessarily have to meet NASA specifications. And then operations costs, a lot of that operation is the responsibility of the payload developer to organize your communication systems, your ground systems, that entire kind of infrastructure. Whereas with hosted payloads, we take care of that for you as a servicer, as an integrator, to provide the operations, the downlink, and that's all coupled in that service. So it's just another facet of the project that you don't have to worry about, and it lets you to focus on kind of your core goal of developing that advanced capability. And then finally, on ground support, just that increased GSC requirements, whether it be fit gauges or whether it be actually in orbit, needing the infrastructure for any sort of like data relay or data downlink. That's not needed. It's a part of kind of that standardized service. So ultimately, hosted platforms reduce the overall cost of payload development, integration, and deployment. So a ton of opportunities there. And so there are some risks, obviously, in rapid prototyping for CubeSats. So JPL, back in 2015, they developed a parts database, which is incredibly interesting if you have time to look it up. And they reported that the majority of parts procured are industrial, automotive, or commercial grade, and few are actually space grade. And there's not necessarily a problem with that, but there is some risk of mission success, right? Because, as they go through qualification testing, there's no consistency among suppliers. And also, a lot of this testing is the responsibility of the CubeSat development team. So while most suppliers do some sort of qualification testing, to what extent? So kind of a few key metrics here. Few suppliers perform lot-specific testing, or 100% screening on flight devices. I think this is specifically true for batteries, and that can play a huge role. And then 40% of suppliers do not verify part resistance, capacitance, and inductance. And again, this is something that is burdened onto the payload developer instead of on the supplier. And so that's kind of taking you away from your core focus of developing that capability. And then finally, 40% of the analyzed suppliers do not inspect for authentic parts. So ultimately, the biggest risk is you have to do that yourself. That's another kind of induced complexity to your program that you need to account for in the development process. So where do I see hosted payloads going? I view it being hosted payloads as a service. So here we're talking about providing everything for you except the, basically except the advanced technologies. So we have the housing, the power, the data, and flexible missions. The biggest thing here is if you go up for 15 weeks and you're like, actually, we have incredible data, we'd like to stay up for another 15 weeks, we'll say, that's fine, let's do it. But we can also return your payload. So if anything fails, we can bring it down, you can inspect it, you can build a more robust system next time. So finally, the ultimate goal here is sustainable and scalable growth. We truly are just trying to use hosted platforms to, mitigate risk, and ultimately I view them as kind of a means to an end. They're not the end itself. The goal is to build robust systems so that we can build strong capabilities for CubeSats and small sats in the future. And some of those key advantages, as outlined throughout the presentation, is that we can reduce program costs, increase swap allocation to the advanced technology, support of non-standard form factors, accelerated path to obtain flight heritage, and the option to return payload after the mission. So ultimately, we're on the balcony. If this is just meant to be kind of a thought experiment. We can discuss where you think the industry is going and where this might play a role. We have myself, Jake, and Cole. I don't think Jake will be on a smock and like a hairnet, but we're up there. So if you have any questions, please feel free to come talk to us. So thank you.
All right. Well, thank you so much, Maggie. Please join me in welcoming Andres from UARC Space to the stage. Thank you.
Well, good afternoon. So today I want to talk to you about reusability of the spacecraft and indeed how we envision the reusability in terms of cargo missions. So first, let's say reusability should be the normal, while disposable should be the rare. In our normal life, we use dishes are made of glass. We don't use disposable dishes all the time, except for rare occasions. So basically in the space, it would be nice to have the same. So for instance, in rockets, rocket companies have found that there is money saving when they start reusing parts of the rocket. Although not all of parts of the rocket can be reused. For instance, second stage normally will stay in orbit for some time until they get burned, generating debris. But what if they could reuse the second stage while it's in orbit? That's SpaceX is trying to develop this huge rocket that will have the capability to re-enter, so they will reuse the first stage right after separating, and then the second stage will be able to re-enter the orbit and then land without any problems. So they probably be reusing most of the rocket or 100% of the rocket. But there are many other rocket companies. Some of them are thinking of reusing part of it, but then we are still generating debris with the second stages. So this is a question for everybody. Can you think on ways to reuse the second stage somehow? Second stage has a motor that is an impressive motor, has a lot of capabilities, could do many, many things. So we should start thinking on ways to reuse those second stage for different missions. But then on regular satellites, we have been start talking about servicing the satellites, but that's not an easy task. So the satellite has to be prepared to be serviced. So there are many satellites that are in orbit since many years that they don't have any type of port to be serviceable. So it's really, really hard to get first to keep where the satellites are and then do some type of service to them. Then the question is, does it worth it to service a satellite that maybe the technology that they have, it's already obsolete? So is it really worth it to do a mission that is so complex to get there, to try to catch the satellite and then do some servicing for an obsolete technology? Here, GEO probably is a sweet spot because geostationary satellites are designed to last for 15 years. They have a lot of redundancies, very expensive hardware. So it's, of course, if you can go there and expand the lifespan of the satellite for 5 more years, it's probably worth it. But still, the missions are really, really expensive. So this is a question for you. When you're designing a spacecraft that has a specific mission that, let's say, it's for 2 years mission, you're going to be taking pictures of the Earth. Do you really need for that spacecraft to be serviceable? Does it worth it to send a mission, to do all the complex operations to grab it and maybe just add more fuel? Probably that's more expensive than the whole mission itself. What happens with orbital transfer vehicles? We're working on our OTV. Most of the spacecraft itself are disposable. They are single-use one. Before we listen to talk of the orbit, and they are doing great things with it, is basically do in-orbit tests, in-orbit demonstrations of different components, which is basically a good way to expand the mission of the primary mission of the OTV, which is go there and release the customers in different custom orbits. Yeah, typically an OTV, if it doesn't have any other thing to do, it's a very short mission, very short duration. Not all of them will have or are planning on having these IoT or IoD missions. So the first question is, what if we reuse those spacecraft? And then how can we do that? How can we reuse a spacecraft that is already flying? So there are 2 options. The first one would be to send a spacecraft that actually has the capability to re-enter the orbit. That's a really, really expensive spacecraft that is massive because you have to have all the thermal tiles to support the re-entry heat. So then you have to relaunch that amount of mass. So it's costly to send, it's costly to develop, it's costly to resend it again to orbit. So still it's good for research activities because you can send something, you can do a lot of experiments, and then you can re-enter and check what happened to those experiments, which is something very valuable. But the second option is to provide the OTB with a docking port, which is basically a way to allow the spacecraft to be serviceable in the near future. After performing some tests, you can say, okay, this spacecraft is still healthy, I can use it, so I will give a go for another mission. After that, I'm going to send a passive lightweight structure that has a cargo container with different other components, other customers for us. And then the space tug is going to approach it, and it will dock with that cargo mission. The cargo will provide extra fuel in case that we need more fuel. And then the rest of the customers to go to different orbits and start deploying them. And then with this, we are actually reusing the whole spacecraft, which is costly, has all the capabilities to be in orbit and to do maneuvering, has a propulsion system, all the sensors, all the computers. And we have verified in orbit that it's still working and it's worth to send a mission to continue. Then the container, which is a lightweight structure, if we release that one, the atmosphere will make it re-enter pretty fast. So we are not generating any more debris. We're re-entering. We are reusing the whole OTB. Now, what is the giveaway? So first of all, you have to think about what is the main mission of your spacecraft. Will your spacecraft have enough capability at the end of life? Is it worth it to add a docking port to think about, yeah, I'm going to send this spacecraft, and I'm thinking already in 5 years to service that to extend the mission lifetime? Then anyway, you should be keeping within the standard interfaces. There are some standard interfaces now for docking. I think Lockheed Martin has released a very good standard on a docking port, which is something that is really valuable for this. And then you have to start looking for secondary mission alternatives. So if you're sending a spacecraft which is has a mission that will only last for a couple of months because you're doing some experiment, try to find a way to do more things on that spacecraft. There are many customers, many institutions, universities who want to do experiments, so look for them and try to put as much as possible on those missions. So reusability, it's very, very important to start decreasing the amount of debris that we are generating in space. And our giveaway is try to deorbit as soon as possible. As soon as you finish with the mission, try to deorbit, and don't keep with the 25 years allowance that they say, yeah, after finishing with your mission, you can stay there for 25 years. That's a lot of time, and we're really congesting the orbits. Finally, this is a very artist impression of type of mission we are working now. Basically, at the bottom is the OTB, and then we can dock with the lightweight cargo mission, which has a bunch of propellant tanks that will give us more fuel, and a bunch of customers who want to go to different orbits. And that is the containers that we will release after getting all the fuel, getting all the customers, and releasing everything. And then another option is that because we have all the communication system, we have computers to process information, we have solar arrays, we have a lot of components for the platform to be an excellent or already proven platform. We can dock with a re-entry capsule that doesn't have all the capabilities that you need. For example, this one doesn't have any solar arrays, it can have only a primary battery, and then we can go grab that one, dock with it, provide all the services that the platform has, do science, and then the re-entry capsule can be sent into the re-entry trajectory to go back to Earth and do all the science. So I think that's pretty much what I have to say. So if you have any question. Any questions? No? Okay. Oh. Yeah. Oh, there are many there. Okay. So yeah, that's a really good question. I think those were other times for space industry were really expensive missions, and I think servicing a spacecraft has to be somehow reserved to those type of missions. So those type of missions that are really expensive, it is worth it to send another mission to do a service to them. Otherwise, I don't think it's worth it, because the cost of the mission itself, the operations, go grab a spacecraft that may be tumbling or something, you have to stop that before grabbing it. It's really, really complex and really expensive. So I think that the lessons learned for that is that it makes sense only for those expensive spacecraft that are out there, like you mentioned the telescopes or geostationary satellites. But it's not worth it for any type of mission. I have been listening people talking about, yeah, we're going to do servicing to all spacecraft, and there's a huge market for servicing. And I say, maybe no, because that's, it's really, really complex and expensive, so it's not worth it for any spacecraft. Any more? No? Okay. Thank you very much.
All right, thank you so much, Andres. Please welcome Austin from Maverick Space Systems to the stage. Thank you.
Hey everyone, how you doing? My name is Austin Krugel. I am the CTO and one of the co-founders of Maverick Space Systems, along with Vitor Koshish and Roland Coelho, who some of you may know. Today I'm going to talk about our 12U tab dispenser, and I'm really excited to share some of the vibration attenuation results that we achieved last year, which are pretty groundbreaking, I think. So let's talk about that. So first, I just wanted to talk a little bit about our company. We're relatively new. We were founded in 2019, just before COVID, so we haven't been to very many conferences yet. But our goal here as a company is to provide cost-effective solutions for launch services. So we do the aggregation for CubeSats and microsats onto launch vehicles, a lot of the integration services, and then we also have product lines too, CubeSat deployers, and we design in-house a lot of the aggregation structures that allow for multiple satellites to be deployed in orbit. Our team has a lot of experience. We have experience with launch sites all around the world, as you can see. We've been involved with over 260 satellite launches, 14 different launch vehicles, 12 different launch sites. So there's a lot of experience to be gained there from just understanding the processing for all those. First, I want to talk about satellite adapter hardware. This is one of the product lines, I guess I'll say, for our company. You can see an example of something that we do here on the left. This was for the recent SpaceX Transporter 4 mission. So we basically take CubeSats and small sats, aggregate them onto a single port location for the rideshare missions, and then make sure all the licensing and paperwork is complete for that mission, and get them into space. In addition to some of the aggregation platforms, we have something called the iCore, which is our rideshare adapter. It's essentially the isogrid structure that you see there. So for smaller launch vehicles, sometimes there's a need to aggregate multiple CubeSats or small sats onto the vehicle. These structures are a way to do that. So that's something else that we offer. Real quick, I want to talk about our other dispensers, other than our 12T that we're going to talk about today. These are our rail type dispensers. So the rail type dispensers are the traditional Cal Poly spec 4 rails, as opposed to the tab type. And for those, we offer our Mercury series, which are the super lightweight ones there at the bottom. Those were designed really for the small class launch vehicles and for just to basically maximize the mass from those systems and allow for more mass to go to the payloads. We have our NLAS, which is based off of the heritage design from Ames, the NASA Ames NLAS, and then we have the Mercury 12 as well, which is a rail type 12U dispenser. So these are just examples of our rail type dispensers. They are fairly low cost and shorter lead times, which is something that we like to offer to our customers. Just moving into our tab type dispensers, which we're going to talk about today, we have a 6U version, the 6T, and then the 12T. T stands for tab, obviously. So the exciting thing that we've incorporated into these dispensers is internal isolation. So, you know, Rise to space can be a violent ride. We've got a lot of vibration environments that the CubeSats are exposed to. And so providing isolation allows for a softer ride to space and lower chance of failure during ascent. So that can be accomplished in multiple ways, and more commonly you would put isolation systems on the outside of a CubeSat dispenser and mount it onto some isolator mounts. That can take up a lot of volume sometimes, and sometimes it's not possible to do. So what we did was we designed something that's actually baked into the inside of the CubeSat dispenser to allow for that attenuation to occur. We still have the clamp boundary condition. If you're familiar with tab CubeSats, the difference is that you have 2 tabs that run the length of the CubeSat from front to back, and the mechanism inside actually clamps on those. And so the nice thing about that is that you have an analyzable boundary condition. If you're running a finite element model, just put in that boundary condition, apply your loads, and you can see what is going to happen dynamically to your CubeSat. These can be mounted either horizontally or vertically, and we have a flight heritage for these scheduled for later this year. So just moving into the 12T specifically and some of our qualification testing that we did late last year, you can see the 12T dispenser there on the right. This testing was actually performed just down the hill at the Aerostructures lab at Cal Poly, so that's kind of fun. That's the Aero Cal Poly shaker. And so what we did was we did a full qualification campaign for the SpaceX rideshare levels. That was all successful late last year. And our goal here was to really, not just to qualify the dispenser, but to characterize what does a CubeSat see inside of the dispenser during these launch ascent random vibration profiles. And so what we did was we put a 12U mass model inside, closed the door, and took off the front access panel to the dispenser, and then put the accelerometer right there towards the CG of the CubeSat mass model to measure the response of the CubeSat. And we captured random vibration data during the test and saw what happened. So I'm going to show some of the results here. The way that we went about this was we thought we need to generate a transfer function, right? So that whatever launch vehicle we're flying on, we can apply a one-to-one transfer function and basically compute what is the result of what the CubeSat is going to see inside the dispenser given on a certain base input at the dispenser, if that makes sense. So the first thing we did was just put a flatline random vibration profile. We ramped up in level, but it was the same power spectral density content from 20 hertz to 2000 hertz. And the reason we did that was because that allows for actually the generation of a real transfer function across the entire frequency spectrum that's typically utilized for random vibration. So we did that, and you can see the results here for, I think, a 3 and about 4.5 GRMS total energy input across the spectrum. You can see the classic raise and amplification at the lower frequencies for an isolator system, and then the dramatic drop-off in energies as you get into the higher frequencies, which are some of the more critical frequencies for designing electronics and other components inside of your CubeSat. So we ran this test, then we generated the transfer function, which is the darker blue line, and we said, okay, let's test this theory out. So we applied that transfer function to a real-world launch vehicle input, to the SpaceX Rideshare User's Guide input, which is a very common one that we use a lot. First of all, the flatline input here achieved a 60 to 70% reduction in GRMS, which is a massive amount of reduction in energy, and very exciting for the community, because this means that you can spend more time focusing on your payloads and devote less mass to your structure. The high frequency stuff is actually mass model modes. That's why they're so sharp and why we cut them off, if you're wondering. Okay, so then we applied the SpaceX Rideshare User's Guide levels to that transfer function, and this is what we saw. So the predicted response is the blue bold line there, and the actual response for two different levels for the Rideshare User's Guide levels are shown there in the green and the blue. And you can see the transfer function actually did a really good job of enveloping and predicting what would happen across the energy spectrum. And so we've actually tried this out for multiple different profiles. And the profiles aren't always the same. It just depends on the launch vehicle that you're on. It depends on if you're on a port that has multiple payloads on it, you're going to get a slightly different input. And so you can take the analysis of these different configurations, plug it into the transfer function, and do a pretty good job of accurately predicting what the CubeSat's going to see during ascent. And the really nice thing about this is that you can do all this analysis ahead of time, so that by the time you go to testing, there are fewer surprises, and you can devote more of your time to to actually testing the payloads on the CubeSat. So for this example, just for the SpaceX example, we had a 7.3 GRMS input, and the CubeSat sees 1.4 GRMS. So that's an over 80% reduction in levels for the CubeSat. And this is an example from the Z-axis. So we have results for all three axes, and they're all pretty similar. So what does this mean? We've talked about some of this. Just to kind of sum up, for the 12T, the internal mechanism clamps on the CubeSat tab, so we have that analyzable boundary condition. That's a really nice thing when you're going into the design phase for the CubeSats. And then the isolation system, which provides the relief in launch environments between 60 and 80%, just generally depending on where the energy lies and in the spectrum. So more mass can be devoted to payloads, less to your structure to make sure nothing falls apart. And the transfer function characterization allows for that accurate prediction. The other thing I just wanted to point out is that we had a customer come to us when we were developing this, and they said, hey, we need more room inside the dispenser. Can you accommodate that? And so we actually baked in a little bit of extra volume inside of the dispenser. And so we can accommodate more volume and more mass than the traditional tab-type dispensers in the market. So that's basically it. I'll stop there and see if anyone has any questions. Yes. I'm sorry, the question is about static loads? That there are other vibration loads? Yes. Yeah. Yeah. So that's a good. So the question is, why are we talking about random? There's other loads that exist for launch vehicles. That's totally true. There's static loads. There's acoustic loads, right? So the reason we focused on this is because traditionally, for CubeSat testing, random is the most severe environment, and it's the one that typically results in the most failures. Since you're containerized, acoustic is less of an issue, and static loads, yes, need to be addressed as well. For static loads, vibration isolation doesn't really play a huge role because it's a quasi-static load. So that's why we focused on the random vibe, if that makes sense. Cool. Any other questions? Not seeing any. Great. If you want to visit us at the booth, we have this dispenser up there. You can take a look at it. So great. Thank you, guys.
All right, thank you, Austin. And now I'd like to welcome Pablo Gallo San Miguel from PLD Space.
Muchas gracias, señorita. Can you hear me? Everybody okay? Waking up? Oh my God, this is dangerous. So they told me to use the micro just to wake up everybody. I think I see some people kind of sleepy. But anyway, I'm going to introduce myself a little bit, and the company where I'm working now is, my name is Pablo Gallego. I am Vice President of PLD Space. I take care of the customers, especially the sales at this moment. And the objective of our company is to provide launch services for micro satellites, small satellite of the size of 450 kilos. That's the typical product we sell. This is a simulation of the launch of our Orbital rocket, which is Miura 5. It's a simulation of a launch from French Guiana, which is the place where we plan to launch the Orbital 1. We like to put always some images of what satellite can do. This is a typical example of Spain. This summer there was a volcano in the Canary Island with eruption. So it took a lot of attention for the general public, and really we want to see this solution. So we think a small satellite can do that. Actually, this size of the satellite who performed this operation is the size of a satellite that can fit in our rocket. I could not put a small video. It's kind of internal, but I trust you. You will not laugh. It was the beginning of our operations. We are continuously working with the team, in improving the operation and the engineering. We like the team to touch the hardware. We are improving every day. So this is one of the first operations we did. You will see this is very hand-on with the team. We just want to run the video. Maybe I make some comments. This is the nose cone of our demo launch. The demo launch is Miura 1. We are installing the nose cone in the upper part of the rocket where we install also payloads. These are our facilities in the south of Spain. Actually, the name of the city is Elche. As you can see, we have the engineering team also doing the integration together with the technician. We think it's very motivating. Actually, everybody asked for that. It's part of the interview. If they want to play with the rocket, they need to do also hardware work. So some people are technicians, some people are engineers, even in subjects that they are not mandatory to be involved in that. That was the first test we did for transportation. And we invite the whole team. We wanted to be sure everybody is involved and also proud. We were bringing the rocket to the testing facility that we own. And here is the team. We prepared the rocket for our testing. And everything that you see there was made by the company I'm representing. This is now a simulation of the Miura 5 launch that is going to be happening in 2 years. This is real. This is an engine test that we perform. And this is simulation from French Guiana. It's a 5 engine in the first stage. Second to first stage separation. Ignition of the second stage. We recover the first stage. You will see some EVTs that are even real because we already test the recovery using parachutes. This was performing the launch base that we are performing the first launch. We recover in the water. We test. We were able to recover at the first shot, and we are very proud because we also have some engines that we wanted to check, the shock and also the possibility of reusability. We have a separation also of a fairing that we perform with our partner RUAG. And we have different configuration of the launchers. We have dual, we have cluster missions, and of course, CubeSat, that we really believe on them. So we are the first micro launcher company in Europe. Actually, we call now the original one because now many other companies are popping up. We're following our path. From day one, our company focused on propulsion. We thought that was the path to go through. The logo is a bull. It's called Miura, like my t-shirt. So it's a good symbol for us and also very kind of patriotic from Spain. These are the different versions of our services. As you can see, Miura 1, which is the suborbital one. Actually, I can go here, maybe. Is the 12 meters high, and it holds the possibility to launch a payload. Actually, the first mission will have 2 payloads. One is from Embry-Riddle and the other is from SARM in Germany, Florida and Germany. It's good for us. It's a risk. It's the first launch, but we want to run the mission management. It's a challenge. Customers are really nice. They are waiting, but they really believe in the opportunity, and also it's a good way to collaborate. We used an engine that is called TEPREL B for the first version of the suborbital. And for the Orbital one, we have the 32 meters rocket. And as I saw in the video, we have 2 stages, 5 engines on the bottom, and I will show more detail on the fairing. Same engine for the second stage is the Temporal C engine with 105 kilonewtons level and 116 at vacuum. This is a derivation of the engine that we are testing now in Miura 1, which is very good for us in order to give us the capability. The reason we performed Miura 1 was to reduce the risk. We wanted to be sure we have a rocket, and we make a rocket with the needs of the satellite, but we wanted to save money. So our investors, we convinced them that that was the best approach. They put money, they see the result, and they put more money. And government is helping us now that they see the product. And from the beginning also they were supporting, especially in the propulsion phase. This is the performance of the launch vehicle. The baseline is 450 kilos. Depending on having a reignition, we could even reach 540. And because of the possibility of launching from French Guiana, we can reach other orbits. Actually, this is our main customer. The main customer doesn't want to go to SSO for us. They want to go to different orbits. We are not targeting the SpaceX SSO. We are targeting the very specific orbit and also the SSO that really want to go in a given time. We sell time. We don't sell, a service as for a cost. So these are the different performance, and the volume of the fairing is almost 2 meters, and the height is 4.5. So we can accommodate most of the small sat that we think reach our orbit on performance. This is, you saw the video, so just a synoptic is a classic approach for a 2-stage rocket with the recovery of the first stage. This is a very good image of our test facility that we built from scratch. We are not renting, we own. We decide the test in the morning and we test in the afternoon. So that's give us a lot of flexibility. Also the team is, very motivated because it gives more access to do things without waiting for the good time. This is the range, the test range we own with the control room that you see here. This is where we test the engines, and this is where we have the stage at this moment. We have other areas to check turbo pump and tanks test, and this is unique. So good images. We do the avionics also. We do the hardware in the loop together. And we do also structures. So you have many good images, more images from the rocket. We saw this image, but I wanted to, and that's very important for us. We have already proved the concept of recovery, something that ESA was very pushing for that. So we got even a contract to do this activity, and we are continuing doing that for the next stages. This is where we are now. We are testing now the suborbital in the test facilities. Recently, we performed all the hardware in the loop on the launch vehicle, and we are now performing some firing tests. You can practice some Spanish now. This is the test we performed 1 week ago.
Director de lanzamiento de todos los operadores, Payload Space Miura 1, listos para el ensayo estático. T-15.
Último interna nav. Encostar
Frecuencia de nav. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, T0.
Ignición.
Presión
down.
Apagado, confirmado. Tiramos antiincendios por seguridad. Despresurización tanques, ok. Aviónica, confirma por favor que tienes potencia externa en aviónica y en FTS. Ground, confirma deshabilitar lanzador para vuelo y deshabilita llave manual 1 y 2.
Deshabilitado.
Todo está safe, parece que el motor está perfecto, el empuje ha sido confirmado, hemos tenido el thrust ok, por tanto hemos tenido empuje nominal en motor, no hay incendios en la rampa, la rampa está también en modo seguro, por nuestra parte parece que el ensayo ha sido exitoso.
Need translation or everything went fine? If not, I wouldn't put the video. Anyway, very proud of what we did. That was a challenge. It happened 2 weeks ago. Tomorrow we will have another test of firing, and the last one we hope to finish this month. So during this year we will be continuing testing more because we want to learn. We will be designing in parallel Miura 5 and changing the design based off the result we have. This is what we have in the manifest. We will be launching in 2022. So this year, Miura 1, Miura 1 also next year, maybe 2 or 3. And then you see the ramp up of Miura 5 compared to Miura 1. We don't see a market on Miura 1, but we keep there as the technological demonstrator. This is the team, very proud of that. And we are now 100 person, and we are hiring in case anybody want to apply. These are the support we are receiving with names and companies. ESA is supporting with especially CDTI in Spain, and also CNES, especially for the launch base in French Guiana, and INTA for the launch base in south of Spain. I just put the last video, if you allow me. It's gonna take only.
What sound does a rocket make?
These are my kids working in Spain. They work even there.
And when it reaches space, there is a complete silence. Nothing can be heard. Then the rocket unleashes the experiments and satellites to make a better world, thanks to physics.
Hardware.
Esto es el motor.
Knowledge. Engineering.
Aquí construyen cohetes.
Menos es más. Dreams. Motivation.
Rampa de lanzamiento.
Commitment.
Dynamism. Keep it simple. Hard work. Teamwork.
PLD Space, we build rockets for everyone.
So thank you, a special thank you to Jordi Puig, that he always say, please don't forget to have fun when you work. I really miss him. And Ryan Nugget from Cal Poly, that really helped me in the process. Thank you very much. Any question? Is there any question, or do we have time? Yeah, this is a LOX kerosene, and for the Miura 1, we don't have turbopump, so we use the COPV for pressurization of the engine. And for the Miura 5, we have 5 engine with turbopump, but the same concept of the engine. Yeah, we are the first company who did the test like that in Europe with LOX Kerox. It's incredible, but the test you just saw is the first time this happened. We are kind of delayed. Yeah, the flight termination system is going to be traditional, at least for the first flight. This is part of the deal, especially when you work in a new base and with a new rocket. And I think this is going to be the plan for the other micro launchers that will be launching from French Guiana. This is, of course, something to validate with the authorities, but for the orbital one is traditional, as you say. Thank you very much.
All right, thank you, Pablo. And please join me in welcoming Chris Lothry from Moog.
Hello. Well, that certainly sucks to follow that because I have no cool videos with the cute, adorable kids. Oh. So I'm Chris Lothry. I'm here to talk about our Slow MV program. It's going to launch out of the UK, and we've actually been talking about it quite a bit, so we're kind of in that last home stretch. So we have a family of capabilities that we've been working on for the last, 8 years or so. We actually started with our orbital maneuvering vehicle in the bottom left corner, and then when we started looking at all the CubeSats and small launch vehicles coming online, we're like, well, hey, they have got the same problems. What could we do? So clever, small launch OMV, slow MV. There's like 50 people in the world who get that. But those are the cool 50 people. So there's about 6 sort of mission cases that we do. The deorbit guys actually have very similar pictures. In fact, all the kind of in-space tug people have very similar. But yeah, it's altitude change, inclination change, phasing, plane change. If you want to do multiple planes, orbit raise, and kind of hosted payload platform, it's different configuration, different capabilities. And like I said, this is actually, this will be the 4th time we've actually talked about this. The 2021, unfortunately, wasn't in person, but 2018 was before we had started our program. 2019 was kind of a status. 2020 was sort of a status. And then there was something that happened in 2020. It kind of slowed a lot of stuff down. So our very first kind of public announcement was July 16th. So this was a announcement of, I kind of got to be careful. So you can go to the internet and you can get all the information off the internet. So you can go to the press releases. But yeah, July 16th, being kind of a space nerd, I was pretty excited because that was actually the day that the Apollo 11 launch happened. So, I can't do the math, but however many years later. A lot of questions, where are you launching from? What are you launching on? Go to the press release. And then a little over 2 years, click. Hey, it's different. The colors are different. The launch site's different. So we had a change there. So we were originally launching from Sutherland, which is the very kind of northern coast of mainland Scotland. So now we're at Saxavord, which is at the very, very tip of the Shetland Islands. So it's a Shetland Space Center. So it's a similar mission. I actually have no idea. I think you have to take ferries and all that kind of stuff to get there. So that's going to be interesting to go. But currently, if you go and read the press release, it actually talks about the rocket and the launch site and an estimate of the launch date. But I'm more here to talk about what we're offering. So we're a big hardware company. So we're actually offering a tug as a hardware solution. So we're probably one of the few companies that aren't offering a service. So if you want to get to space, I'm not actually the guy to talk to. I'm more or less you've got a mission, you're trying to put it together. There's the 6 things that we can do, help that figure it out. But yeah, we don't really do anything with the launch vehicles. Obviously we got to work with them. So I'm not usually, I'd say, all that relevant for a lot of the kind of academic or even commercial. This is more focused on more governments where they kind of want that ownership and the ability to sort of tailor and flex things. But if you look block diagram-wise, wow, this is suspiciously like a satellite, because that's effectively what it is. And for everyone, we started doing this in kind of late 2016. I think we were one of the first people out there actually doing it for this size. And now today, there's a whole bunch of people. In fact, many people that have been flying deorbits probably out there ahead. And it is a challenge, because you're designing a spacecraft that is bigger than a CubeSat. It's more capable, usually more power, bigger propulsion. And you really yourself have to be more reliable, because you can't be less reliable than the things that you're trying to drop off. So you add all that, but you still have the cost and mass and schedule pressure that the CubeSat developers have, because, kind of limited funds. So it created a bit of a challenge. Just some kind of specs. Yeah, we're 2 foot by 2 foot. In fact, our solar array is just slightly bigger than the DISSat that was brought up here. I think it's out at the NASA booth. Give you an idea of the size. We're about 130 pounds. And because this is a kind of a joint US-UK effort, we're actually working under a grant. Part of our commitment, our corporate commitment, was we were actually going to try to do about 55% or more of the work back in the UK because, you know, it's kind of not like, you know, good pool to take a bunch of money and funnel it into the US. Unfortunately, we actually have a lot of capability already in the UK. There's actually a pretty decent supply chain there. And there were some where we actually had to go out and actively build up capabilities. So just a few of our UK vendors and partners. So we have our propulsion systems going to get put together in our, or not ours, NAMO's, it used to be ours, Westcott facility. So that's actually going on right now. Solar array from AAC Clyde. Battery from ABSL, Pentaxia is our structure. They actually didn't make spacecraft structures, so this is new to them. New Space Systems, they're kind of based in the UK, and then we're going to, we actually stood up a facility at an existing site in Reading, so they weren't even a space facility, and we built them out to become a space facility. A lot of the environmental testing is going to be done at Harwell, which if you're familiar with the UK, that's kind of like the big central space area. And then we've had a lot of systems integration support from a company called KISP. They're actually a bunch of ex-Surrey folks, so they're very familiar with the small sat industry. So it's kind of a simple bits and pieces. They all kind of go together. This is kind of graphically showing it. Not everything could we source from the UK, so we do actually have American parts. So we have a handful of things, and we use this as sort of a development for ourselves because this is our first integrated spacecraft. So Moog's been around for 70 years, but we've never actually done anything like this. So we started looking at, could we actually use this as a platform to demo new technology? So we actually have, for us, a new set of avionics that are actually derived from big GEO class avionics, but, you know, made smaller, cheaper, lighter, faster, all that kind of stuff. Our prop system, we have a green propulsion system. Every single component, almost every single component, and it's actually new, trying to go after, once again, smaller, faster, cheaper, lighter systems. So there's a lot of firsts in this, which I don't recommend doing as many firsts as we did at once. If you're new, that is, you know, we have a new facility, a new rocket, a new launch site, a country that isn't set up to actually do launch yet. You know, all these things going on in parallel. And then you have COVID, and then we actually had to deal with Brexit as well. There's licensing. There's all kinds of fun stuff. But these are actual pictures taken, a few of these within just a couple days. So you've got our composite structure. The cylinder makes sense for, you know, rockets because everyone puts boxes in the cylinder type launch vehicle. So that made a lot of sense, but it turns out everything else that you then put in the cylinder are all boxes themselves. So we actually ended up with a lot of intermediate structure just to kind of adapt that cylinder to box type structure. In fact, we've actually looked at this. If we had to do it all over again, we wouldn't even do a shape like that. We'd actually do like a hexagon or even an octagon, and then you can actually just do kind of box to flat panel. Solar arrays, there's not actually a lot of circular solar arrays out there, so that was a custom one. It's very similar to an existing rectangular one. Propellant tank was actually new. Our CubeSat dispenser is actually new, and I've got a slide on that. So when we started going down this road, we had a pretty tight mass restriction, and obviously we couldn't gobble up all that mass. So we started looking around, and heritage kind of CubeSat dispensers are actually pretty heavy, and we've got 6 of them. So we're like, man, if we could even shave just a few kilograms off that would actually allow us to carry an extra spacecraft. So we ended up, I think we worked with Maverick, so they're a local company here. They've actually got a booth. In fact, the 6U here, they've got one out at their booth. So we were their first customer for that. And this saved us about 12 kilograms, so about 6U spacecraft we got to add back in. So some pictures of them doing testing. These are actually old. What else? Our Reading facility. So this is an existing Moog facility where they actually do things for the aircraft and military ground vehicle industries. And when we started going around in our facilities in the UK, it turned out that, you know, weapon platform things for attack helicopters actually have a lot in common with space. So it actually was a pretty good fit. And they happened to have a chunk of their facility that was kind of open, so they leased it. We built a mobile clean room. This picture is actually a little bit dated. They got a lot more. We've got an environmental chamber and a bunch of other stuff. And then, yeah, we've been kind of marching along. You know, you go to a CubeSat conference and you talk about how you've been working on something for 4 years, and it was 2 years of work ahead of time, and they just kind of roll their eyes. But for a first of its kind and all the firsts that I kind of listed off, we actually think we've done pretty well. We've bounced around between our launch vehicles and our launch site, so that actually has changed things. So that sort of slowed down things. And then obviously COVID didn't help and some other issues there. But yeah, we're in production right now. We actually delivered to our customer, Lockheed Martin, summer, fall this year, and then it goes out to the launch site. And then I think I'm the first person to actually put up a slide. I'm not just going to say we're hiring people. So this is actually more for our US folks. So yeah, if you've been in the industry for a handful of years, especially software, GNC, program management, you know, we don't care if it's CubeSat or SmallSat or anything like that. But yeah, we've got at least 10 or 12. We're based outside of Denver, so a little bit cheaper than California, although probably not by much. So summary, we've got our line of orbital maneuvering vehicles that can do all kinds of interesting missions, rideshare or dedicated. In our case, we're a dedicated rideshare, whereas we're the primary payload, but we're carrying 6 random payloads. We're currently under production. Our customer that's kind of in the public domain is Lockheed Martin. And we're going to be launching on the ABL RS-1 out of the Shetland Islands. And then, you know, we basically took existing stuff and kind of what could we do to make it cheaper, lighter, faster. We didn't want to start from scratch on anything, so everything sort of like is derived from something existing. And then, yeah, we've got, you know, we've got through all our design, all of our production, or not all of our production, but we're getting into all of our production, and then we're hiring. So if this sounds like it would be fun, reach out. Website, email, phone, probably the only idiot to put their personal phone on a big slide in front of people. So call me, text me, email me. Any questions? I think there's one back there. Yeah, so actually the bottom interface is a 24-inch diameter. We fly a light band, so actually it would fit on an Espa Grande. The overall dimension's about 40 inches, so an Espa Grande is 42, 46 by 56. So we actually fit on an Espa Grande. In fact, we can actually be double stacked and still fit on an Espa Grande. So that was part of the idea of having this kind of compatibility. So I'm not showing it here, but imagine these clusters where you have either an Espa or a propulsive Espa, which then has 5 ports with 10 of these on there. Each of these then have, you know, 6U CubeSats. So you kind of get into that whole like nesting doll type capabilities. And we put that forward. It was like no one had any ideas of how you would use that because that capability's never really kind of been out there. So it was like, wow, that's really interesting. No idea what you would do with it. So if you've got ideas for it, that seems like it would be cool. Any more? I only got a couple more minutes. So that is not a straightforward answer because we drop off payloads. So notionally, we've got about 200 meters per second delta V capability. So we're LMP-103S green propellant system. We hold about 13 kilograms of propellant, and loaded we're about 165. So, you know, if you drop 5 payloads off right away, we got more. If you carry all 6 to somewhere, we got less. So our baseline mission that we're doing is we're actually going to we'll launch to an altitude. We'll deploy a spacecraft, deploy another spacecraft, go to a different altitude, do the same thing, and then go to a third altitude, do the same thing, and then we'll actually bring down our perigee. So part of our mission is actually the active deorbiting, because that's a big thing with the UK. They didn't want to stand up a new policy, a new kind of regime, and have like the 25-year rule is just sort of be like a thing. So they're actually pushing really hard to, get out of the way fast. So yeah, we've actually got a really short mission for the capability that we have. We could stay up much longer, but the deorbit is actually part of the mission. So anything else? Okay. I will yield my time to the rest. Thank you.
All right, thank you, Chris. Next, we'll be hearing from Jason and Vikram at Adaptive Launch Solutions.
Good afternoon. I am Jason Smith, and this is my colleague Vikram Krishnaswamy. We're here representing Adaptive Launch Solutions. We're a small company based out of San Diego, California, that performs launch service integration for a variety of space vehicles. And you can see some of our work on the right-hand side for the Landsat 9 ESPA flight system mission, or EFS for short, where we grappled with a potential problem with recontact for our payloads when we deployed them into orbit. We developed a partial solution there, and we've extended that solution into what you'll see today. So large rideshare missions like the SpaceX Transporter mission, which has been referenced quite a bit these past couple of days, and the Ariane Space VV-16 mission are becoming the future for both commercial and government launches. We started with what are the requirements for recontact, and we found that requirements were for the individual satellite through the Orbital Debris Mitigation Space Policy, and for low Earth orbit, that collision probability must be less than 10 to the minus 3. Now, this also is mainly for high energy collisions, but any collision is an issue. In large rideshare missions, a lot of the controls are not on the satellite side, as they are inhibited for system safety reasons, or they cannot perform a propulsive maneuver. So most of the control for that mitigation for the risk of recontact lies with the launch vehicle and or flight system.
So that led us to the question, how can we best exercise that control to reduce the risk of recontact for the satellites? In order to answer that question, we built a study around a hypothetical model of a mission going to a sun-synchronous low Earth orbit. As you can see, that mission contains 23 satellites of all shapes and sizes, from a 1U CubeSat all the way up to an ESPA class. And those satellites are arranged around the various ports of the ESPA ring. Some ports have 1 satellite, others have up to 8. With the mission configuration defined, we do this before any analysis occurs to emulate the typical integration cycle. We then start inputting the parameters of this mission into our rapid analysis tool. We constructed this to allow us to perform these analyses out of cycle with the typical launch vehicle load cycle periods. So that allows us to be more flexible with our satellite payloads. Those parameters which we model include over 120 of them. They're specified with the nominal values and the 3 sigma uncertainties, and they include variables such as the orbital parameters, the launch vehicle attitude at the point of each deployment, the satellite mass, and the deployment system energy for each satellite. So with these parameters defined, we then needed to be able to determine a risk of recontact for any given close approach on a simulation. We do this by assigning each satellite a unique covariance ellipse. Now, in our scenario, which is a little bit different from most, these covariance ellipses start out extremely small. All of the satellites are located perfectly with respect to one another at the beginning. As they leave, those covariance ellipses sizes are determined based on the size of the satellite and on how far the satellite can move due to disturbance forces that they may encounter. With those covariance ellipses defined for each satellite, we can then look at each close approach and determine how likely a recontact is in that situation. Given that likelihood, we can sum that up over the course of the entire mission and develop a total mission risk. That mission risk can vary based on those input parameters, of course, so we construct a Monte Carlo and run that at each given launch vehicle attitude and deployment sequence timing. Now, if we were to do this for all of the attitudes we'd like to see and all of the timings we'd like to look at, that'd take us about 5 years. Wholly unacceptable. So in order to avoid that, we're clearly going to have to develop an intuitive understanding of the problem to reduce the number of simulations we have to conduct. Our first guess at that understanding, our hypothesis, was that satellites would mainly collide with one another because they aren't really moving apart. In fact, if we don't cause that to happen through our actions, those satellites are going to stay in roughly the same position. So imagine a couple of cars driving down the highway. Those cars are most at risk for colliding with one another. if one is tailgating the other for a long period of time. We would prefer them to be moving apart, and if possible, we'd prefer them to start off at a decent distance from one another. So in our case, for the satellites, we can cause those satellites to move apart. We can do exactly what satellites do to meet each other, just in the opposite direction. We can cause orbital phasing. In turn, we can do that by changing the semi-major axis of each deployed satellite. That can be accomplished by affecting the prograde component of their separation velocity. You can see how we tried to do that on the Landsat 9 EFS mission that my colleague mentioned on the right-hand side. So, laser, there you go. The vertical axis here is the prograde component of separation velocity. Here you can see there's 4 satellites on port 2, 2 satellites on port 4, 3 satellites on port 5, and etc. Those satellites, which are located on different ports, we would like to prevent them from having any horizontal overlap between their prograde components of velocity. This will mean that they eventually move apart over time. As you can see, that's much more difficult to accomplish for satellites on a port than for satellites on different ports. That leads us to our 2 first predictions from this heuristic, that for satellites on different ports, we would like them to be moving apart due to orbital phasing. And second, for satellites on the same port, since that isn't really possible, we would like them to have a large initial spacing and to deploy in decreasing order of separation velocity. Finally, our 3rd prediction, because these satellites on different ports are phasing apart, it shouldn't really matter what the initial spacing is, so you can deploy them as quickly as you want. Given these 3 predictions, we should be able to reduce the amount of simulations that we conduct and thus get an answer in a reasonable amount of time. That said, we do still have to figure out, are these predictions actually correct? We did that in 2 parts. First, we looked at launch vehicle attitudes, and second, at the deployment sequence timing. So on the left, you can see how we verified predictions number 1 and 2. First, we angled the pitch of the launch vehicle at 30 degrees from the orbital velocity vector. Then, at that attitude, we rotated it through 360 degrees of roll. We repeated that process at 60 and 90 degrees. So as you get further away from the orbital velocity vector, you should cause more prograde velocity, and thus more orbital phasing. Because of our first prediction, you should expect that as you move in that direction, we see less recontact. In the same sense, as you roll the launch vehicle, the different dispensers on the different ports should have increasing and decreasing risks of recontact. So we expected a strong roll angle dependence in the graph you can see on the left. The text is a little bit small, but on the vertical axis, we've got the logarithm of the expected number of satellite collisions per launch. And on the horizontal axis, we've got the roll angle. We didn't expect the dependence of the chance of recontact on the roll angle to be quite so sharp. Likewise, we expected the pitch angle dependence to be more prominent. What we see here is that if you get it just right, or just wrong, I suppose, you can expect up to 25 collisions per launch in just the first 3 orbits in our given hypothetical scenario. In single simulations, we saw up to 130 in that same time period. Now, if you look just 15 degrees away, we have a collision risk of 0.01 per launch. Clearly, the roll angle is important, and if you look at the data that produced this graph, we find that these collisions are more likely on satellites of different ports. It's very unlikely to see satellites on the same port collide. So that's our first 2 predictions. Prediction 1 is a qualified success. We do need orbital phasing, but maybe it's not a straight correlation between more phasing and less recontacts. Our second prediction was true. We didn't see any collisions when we took that into account. Finally, if you look at the right-hand side, we tested the deployment sequence timing prediction. We took the best and the worst case attitudes from the graph on the left, and we decided to change the deployment sequence timing. Now, we expected, per our prediction, for that graph to be flat. As you can see, it is not flat. Our prediction was very wrong. Clearly, timing is still an extremely important factor in making sure that satellites don't collide with each other. It bears mentioning that these deployment sequences are not particularly long in any case. We go from 2.5 minutes to 6 minutes in the graph you see there. So with these predictions tested, that means that we can find and react to situations that would cause the satellites to contact each other ahead of time, and thus prevent this from being an issue. With that said, I'll give it back to my colleague.
So we bombarded you all with a bunch of technical information up front. So here's the takeaway. You need a combination of both orbital phasing and initial spacing in order to minimize and reduce that risk of recontact for these large rideshare missions. The tool that we created allows us to quickly change that manifest and perform these out of cycle, which is a benefit to flexibility for these missions. Now, an impact on the launch vehicle can be shown through optimizing that deployment sequence to reduce the overall need for the launch vehicle to perform station keeping and perform its mission duration. So we do have some work cut out for us for the future, and we'll be applying this on all of our future missions going forward. With that, we've come to the end of our presentation, but we do have some time for questions. So are there any questions from the audience today? Okay, seeing none, thank you all for your time, and if you want to reach out to us, we'll be here the rest of the conference. Thank you.
All right, thank you, Vikram and Jason. Next, we will have Lily, Alice, Paul, and Paul from DX Hub.
Welcome, everybody. We thought we'd have a little anticipation waiting for us to come out. Welcome. We're really happy to be here today, and we're glad you all are joining us. I'm Paul Jurison. I'm the director of the Cal Poly Digital Transformation Hub. And the Digital Transformation Hub has a partnership with Paso Robles to work on the Spaceport application that they're working on. And we want to talk a little bit about that today. But first, I just want to take a minute or two to talk about what the Digital Transformation Hub is. The Cal Poly Digital Transformation Hub was formed about 5 years ago to work on challenges that the public sector has on some of the biggest problems they have out there. So we're a partnership between Amazon Web Services and Cal Poly. Amazon provides us with resources, both personnel and in-kind resources, and we work with lots of different public sector organizations to solve many problems that we have. Well, what our real goal, though, is to get our students real-world experience in working with real customers on real problems using the latest innovation processes and technologies, and how we can apply those technologies to real-world problems. So our students get that experience before they graduate. We think that's a big advantage for them. Some of the areas we work on, as I mentioned, is public sector digital transformation. That's one of our top topics. We work on cloud innovation development, so we apply cloud technologies to problems to help solve them. International development is a big area that we work on quite a bit, and World Bank is a big customer of ours there. We have 20 or 30 projects with World Bank around the world that we work on with them. Space operations innovation is another big area that we focus on, and that's what we'll talk about today. Paso Robles is one of our customers at the Digital Transformation Hub, as well as Vandenberg Space Force Base and the Space Force in general. And workforce development is another area that we look at. We really, again, as I mentioned, we really want to get our students real-world experience before they graduate, and that's part of the workforce development effort we work on. So, without saying much more, let's talk about the topic at hand, and I want to introduce Paul Sloan, the Economic Development Manager from Paso Robles, and he's going to talk about the project that we're working on.
Thank you, Paul. So my name is Paul Sloan, and I am the Economic Development Manager for the City of Paso Robles. And just as a bit of context or background, if you're not familiar with Paso Robles, it's a lovely little town about 25 minutes up the road where we have beautiful year-round clear skies, and we also have over 300 wineries. So there's several reasons to visit Paso. And our economy is primarily focused very much so on the wine sector, but also on the tourism which comes with the wine. And so we're very pleased with that. But one of the priorities of our city council has been to diversify our economy for a couple of reasons. To continue supporting those two very important sectors, but to diversify for better long-term stability economically, but also the wine and tourism sectors tend to skew towards service-level jobs, which don't always align well with the cost of living. So our goal is to work to attract higher-paying head-of-household jobs, and for that reason, we began looking at the world of tech. So there's an organization here on the Central Coast called the Regional Economic Action Coalition, or REACH for short. And REACH, in partnership with Cal Poly, as Paul said, and other organizations, they advocated very strongly for the conversion of the Vandenberg Air Force Base to the Vandenberg Space Force Base. And those efforts were successful, as we heard yesterday from the 18th Space Control Squadron in their great presentation yesterday afternoon. So that transformation helped bring the focus once again to the West Coast for the space sector. So sitting in Paso Robles with Vandenberg to the south of us and Silicon Valley to the north of us and Cal Poly right here in our backyard, the question became, what, if anything, may be the possibility for Paso Robles to participate in the emerging Central Coast space economy. So about a year ago, there we go, our mayor, Mayor Martin, tasked us with researching to study the potential to utilize the existing infrastructure, it's a key word, and resources to create an opportunity to align with the REACH space effort, which is that regional economic organization, to create jobs that align with the development of the space sector and the developing tech corridor, and I'll come back to that word in just a bit, with the mayor's goal specifically to optimize the city's potential to participate in regional development plans, specifically in the area of the growing global commercial space transportation industry. When we talk about existing infrastructure, I'm referring to that big runway that you saw in the very first slide. And so that's what we started looking at. And so in partnership, working in collaboration with the Vice President and CIO of Cal Poly, Mr. William Britton, we began researching what may be the potential for Paso Robles to become a spaceport focusing on horizontal launch. So this is a slide that all of you, I'm sure, are very familiar with. There are 13 commercial spaceports in the US currently, and only one in California out in the Mojave, actually the only one on the West Coast. And so we, with Mr. Britton, we began speaking with FAA, Global Spaceport Alliance, to see what may be the potential for us to become a spaceport in Paso Robles. So the steps that we've followed, I'm probably aware, there's basically 2 steps with the FAA. First, you tell them the kind of spaceport that you want to be, and that way they know how to go about authorizing you. So we put together a spaceport plan, and this was approved by our airport commission as well as by our city council. And so last August, I went to the FAA, and they came back to us and said, great, now we know what kind of spaceport you want to be. And so this is how you go about the application process. And so that takes us up to about the 3rd line right there. And at that point, we knew we needed to kick it up a few IQ points or more. So Mr. Britton connected us with the wonderful folks at the DX Hub to work with us on the much more detailed process of getting the application in for a full spaceport license. After that, we're going to work on developing a full economic plan and see down there, build out the tech corridor. So what we're pursuing right now is a dual track approach. We're pursuing the spaceport license, but also we're developing a tech corridor to develop and attract all of the many, many businesses like this that we see here at this conference to build a cluster or a hub of all the industries around that. On the tech corridor side, we have several hundred acres on the airport proper that are available for lease, but also adjacent to the airport, we've identified about 2,000 acres that can be built out specifically for industrial parks and tech parks. And we have several developers we're working with now specifically on that. One example, if you want to check it out, it's called the Paso Commons. You can look it up online, pasocommons.com. It's a great example of what we're building out in the tech corridor. It's a 22-acre campus, 7 buildings, 400,000 square feet under roof, build to suit. So that's what we're pursuing on the tech corridor side while we work with the DX Hub folks on the spaceport side. And one last thing, I would like to give a big shout out and thank you to Mr. Ryan Nugent from the CubeSat lab, who provided the city of Paso Robles with a model of the ExoCube 2 CubeSat, which we have on display in the city library up in Paso Robles. And our library staff is thrilled to be working with the faculty and staff of Cal Poly to develop educational programs about space technology, which we will be rolling out in September. So I can say that up in Paso Robles, the very lovely little town, 25 minutes up the road, our vocabulary now is Cabernet Sauvignon, Grenache, and CubeSats. So with that, I'll pass it over to the smart people.
So I'd like to introduce a couple of our students that are working on this project and have them talk a little bit about the work they're doing and how this is working with their academic education and their future. And let's start with Lily. Lily?
Thank you all for having me today. My name is Lily Turkstra, and I'm a 4th-year research psychology major here at Cal Poly. I've been working with the DX Hub for a little over a year as a student project manager, and I've had the amazing opportunity to work on several challenges such as this one. I currently also work part-time with Boeing, and will be looking forward to joining NASA this summer in the Human Health and Performances Division. So as Paul spoke about earlier, we've been going through this licensing effort to create the spaceport in Paso Robles. We've been working with the DX Hub in combination with Paso to complete this FAA application to fully transform the airport into a functional spaceport. So this application in itself is a comprehensive and lengthy document that details everything from potential trajectories all the way to potential risks on the runway, all in the name of human safety. In this effort, we had the opportunity to speak with Dr. George Neld, the previous FAA Associate Administrator for Commercial Space Transportation. He was responsible for the licensing and regulating of commercial launch activities, and he was also recently a crew member on the Blue Origin New Shepard launch. So his insights and experiences gave us very valuable information to help continuing this project. We're working on filling out this application and hope to have it complete in the coming months using dimensions from Concept X-planes. We are also currently working with industry experts such as those at Wagner Star Industries, as well as Cal Poly faculty, which my colleague Alice will discuss next. Thank you.
Thank you, Lily. Alice.
Hi, everyone. I'd like to thank the Cal Poly CubeSat Lab for having us all here today. My name is Alice Dukostovsky, and I'm a third-year aerospace engineering major here at Cal Poly with a concentration in astronautics. I started working at the DX Hub over a year ago as the lead project manager there, and over the past few months, my work has focused on the Paso Robles Spaceport project. Specifically, we started working with the city of Paso Robles to complete the FAA Spaceport application and licensing process. And I was delighted to have the opportunity to work on this project, which will allow the Central Coast to grow economically and launch CubeSats into orbit at one point. The FAA Spaceport application and licensing process is obviously very lengthy and meticulous, and therefore the application before the application was started, Paso Robles completed an engineering review to ensure that the project was even feasible. And we hope to have this application filled out with the help of Concept Explains Dimensions in the coming months. We're currently working through this with industry experts and Cal Poly faculty and recently Cal Poly Aerospace Engineering Professor Dr. Akira Abercrombie, and who has joined us to give us insights as we progress. The FAA, essentially for the Spaceport application, requires extensive propulsion data, trajectory data, apogee data, so we're very grateful to have the support of Cal Poly faculty on this project. We hope that the Paso Robles Spaceport will diversify the economy and create a thriving aerospace industry on the Central Coast, and hopefully one day launch CubeSats into orbit. Even though there are only 13 commercial spaceports in the United States, Paso Robles Spaceport has the opportunity to make a big impact in the aerospace industry. Thank you.
Thanks, Alice. I don't know if we have time for questions, maybe for one or two. Does anyone have any questions? I see one back. Yep, the contact information should be on the screen. Yep, great. Others? There's one in the back. What's the timeline look like for this? Paul, do you want to address the timeline?
We have an estimate timeline of about 28 months if things go according to plan. There's many, many steps in this phase, but that's sort of how we've mapped it out, give or take. So we're looking at potentially achieving a spaceport license sometime in mid-2024.
Great. Yes. Around the airspace. Paul, do you know the answer to that one?
I know the answer.
Alice knows the answer. Alice will answer.
Oh,
Go for
okay.
it.
Yeah, I was just going to say that, well, basically it'll still function as an airport, but on days they're launching, horizontally launching these space planes, they would just put a temporary flight restriction in the area. So it wouldn't function as an airport on those days, but it still plans to function as an airport normally.
Great. I think we're out of time, right? Okay. Yeah, we're out of time. Please feel free to contact us if you have any other questions with the contact on the screen, and I think we'll be around here for a little while, so you can come find us. Thank you.
All right, thank you, team from DX Hub. Next, we will have a break and poster session. You can visit the third floor to view the posters and speak with the authors of the posters. We would like to thank Skyline Celestial and DHV Technology for providing the snacks and beverages outside, and we will start back up at 3:30.
Hello, everyone. Welcome back. We would like to thank Millennium Space Systems for this afternoon's food and beverages, and we have a video from our sponsor.
Curious, bold, clever. That's who we are at Millennium Space Systems, a small satellite company that is fast-paced and innovative, building satellites in months, not years. Our team comes up with clever ways to revolutionize space. We take risks, challenge the status quo, and embrace commercial technology. Because the missions we support matter, our work safeguards what's important: people. And when we launch and operate our satellites, we know each one of us made it happen. At Millennium Space Systems, you have the opportunity to grow your career in the direction that's right for you, in an environment that's open, inclusive, and collaborative. Are you ready to help accelerate the small satellite journey to space? Join us, channel your skills, and contribute to a greater purpose.
All right, up next, I would like to welcome Miguel Vasquez of DHV Technology.
Hello, good afternoon, everyone. It's really a pleasure to develop this talk today. Let me introduce myself really quick. My name is Miguel Vasquez from DHV Technology. I'm the managing director and co-founder of the company. The talk today is entitled COTS, Solar Panels and SADA for CubeSat. First of all, I'm going to comment in a couple of slides the activity of our company, and later on we'll develop. We share with you the products we developed for CubeSat applications. DHV Technology was founded in 2013, 9 years ago. We are 3 founders, and we are focused on power system for space applications. We have developed a complete power system for CubeSat platforms, and we have a relevant experience on a small satellite platform and another type of space application like rovers and so on. Right now we are a company of more than 100 people. Majority of them are engineers, as you can imagine, are space, electrical, electronic engineers. And the founder, we are three founders. 2 of them, we are a PhD in physics, and the third is industrial engineer. And right now we are in a building of 3,700 square meters. And right now we have facilities, a clean room of 1,200 square meters of 5.5 meters of height. That this allowed to us to develop big solar panels, solar arrays, deployable tests, and so on. This is what we do. We develop power system for space application. Talking about CubeSat, we have developed standard solar panels, as you can see in the slide, for 1U until 6U, 12U, etc. Our approach is to develop customized products. We receive the requirement of our customers, and we adapt, so we customize our products to the mission. In addition to that, we think it's a good the customers, the sector demand some standard products, some COTS products, talking about solar panels specifically, and we developed this line of products. These solar panels, as I explained I comment in a few slides, are compatible with the majority of the structures are in the market and so on. So in addition to the solar panel, we have developed SADA system, solar drive assembly for CubeSats, for 6U, 12U, and 16U. And we developed the electrical power system, the EPS, for a different range from 1U until 6 and 12U. Okay. The first project we have been involved was flight in 2014. This was a small satellite project. It's called UNISAT 6 from Gauss. It's an Italian company. From 2014, we developed more than 200 projects, and right now there are about 145 satellites working with our products. We are working with different companies, working at constellation level and recurrent projects like Spiral, ISI, Astrocast, D-Orbit, etc., in Europe and USA mainly. For sure, we have customers in South America, South Africa, South Korea, Japan, and all other countries, but our main market is Europe and USA. In fact, our main market from 2-3 years ago is USA, our private companies, NASA, and universities. This is in a nutshell the product we are going to describe to share with you today. A standard solar panel for CubeSat, SADA system, and EPS. Talking about the solar panels, as you can see in the slide, the mechanical interface, we analyze different structure in the market, and they are comparable with the majority of the most common structure. So you could integrate in your platform if there are some of the most common platform in the market. We use true projection solar cells, state of the art, 30% efficiency, bypass diodide to protect the solar cells. Typically, we use photodiodide as a sensor if it's required, and as option, we could include the magnet torquers in all the solar panels. We have a magnet torquer option, a version with magnet torquer embedded in the PCB. You could connect with your attitude control. In addition to that, let me comment that this approach is similar. As you can see in the slide, this is the power and so on, and the mass, estimated mass. The features are similar to you. Modify the shape and the number of solar cells and the power for 3U and for 6U. Okay. The next product I'd like to comment with you is the SADA, Solar Array Disassembly. We developed 2 versions in 10 millimeter of height and in 60 millimeter of height. It's a quite compact approach. It's a gimbal for one axis. The communication protocol in this version of 6U is I2C. And the solar rise, you can see, is in roughly about 100 watts. Okay. We provide this product to NASA Goddard. We develop at the moment 3 projects with NASA Goddard, Snoopy, and GTOSat. We provide the solar panel for these 2 missions, and in this mission, it's called Dion mission. We provide the deployable solar panels and this CubeSat, this product of 10 millimeter height. In addition to that, we are developing a 16U CubeSat SADA, as you can see in the slide. So the form factor is a bit different. The height is a bit it's higher. And the power we could accommodate in the solar arrays is in the range of 160 watts. Okay. The communication protocol in this case is we have 2 options: CAN bus or I2C. depending of the customer requirements. And this project has been developed under ESA contract, the European Space Agency, and will finalize at the end of this year. In October, November will be finalized. The next product I'm interested to share with you is the EPS, the electronic power supply. We have a couple of products for CubeSat. The approach is a modularity design. So we have one motherboard, and we could have one or two daughter board. So in this case, the product you have you see in the slide, the Pico EPS, is designed for a 1 or 2U CubeSat. The maximum input power is about 60 watts. And you can, as you can see, we could we developed this product, take into account for sure the PC104 form factor, and we developed a specific qualified for ISS. So we are work with nanoracks, and we follow the guidelines of nanoracks, and we develop all the tests to assure the operation in the ISS. In addition to that, in the next slide, you can see the nano EPS is focused for CubeSat from 3U and 6U, or in case of deployable in 2U or 3U. Okay, so in this case, we could manage until 80 watts. And in this case, we have, for example, one motherboard and two daughter boards. Okay. The rest of the future are similar. And finally, I guess I'm on time. Finally, in this slide, we show some of the missions where I commented before, and I like to comment with you what type of product has been developing in each of one. So in this mission, this is a 12U. This is a double deployable. We develop in this project is Argo Moon mission. It's a deep space mission. Will be in a flyby of the moon inside the Artemis. Is one of the CubeSat mission in Artemis 1. Is the only European mission, as you know perfectly. In Artemis there are 10 USA projects. 2 projects from JAXA and 1 project from Europe. This is the Argo Moon mission developed by Italian Space Agency and ESA. In this mission, we provide the double deployable solar panels. In addition to that, we develop for the same company, for Argodet, Italian company, we developed the solar panels. It's a similar approach of that. Lycia Cube mission is another deep space mission will be close to asteroid. This is the first MEO mission we developed. This is a body-mounted solar panels. The mission is called TriSat-R. Has been developed by Maribor University in Slovenia and has been funded by ESA, by the European Space Agency. Has been launched already launched. Argo Moon will be launched hopefully in a few months, and Lycia will be launched during this year probably. Angels missions was developed for Kenes and Emeria, the French company and the French Space Agency. It's a double deployable. It's based in this design, but is a bit different. This is a LEO orbit. This mission is a 12U, as you can see in the slide, and is for Earth observation. And the payload is from Thales Alenia, and we provide the body-mounted and the double deployable solar panels. In Neptuno mission is a Spanish mission. The prime of the mission is Deimos Space. We provide the body-mounted and double deployable solar panels and the EPS. So the Pico EPS we share with you in the previous slide has been test and has been flight in this mission. It's already flight last November. And finally, this is the 3 projects we developed with NASA Goddard, GTOSat and Snoopy. This is the body-mounted and double deployable 3U form factor of the solar array, but the CubeSat is a 6U. GTOSat is a mission, a scientific mission in a GTO orbit to analyze the high-energy particles. And finally, a Dion mission is a LEO orbit. We developed the SATA system and the triple deployable solar panels and has been already delivered to the customer, to NASA Goddard. Okay, so that's all. So thank you so much for your passion. This is my email, and I think there are some couple of minutes probably for questions. Thank you so much. Yes, please. Yes, absolutely. It's a really good question. Yes, we develop a thermal manage. In the previous slides, I comment that we have a power manage and battery module in the same PCB. And yes, we develop a thermal manage of the batteries. Yes. Yes, exactly. Any other question? Okay, thank you so much.
All right, thank you, Miguel. Up next, we have Darren Wallace of NASA MSFC Payload Mission Operations Division.
Having me today. My name is Darren Wallace, and I am a operations director at Marshall Space Flight Center for small spacecraft. My colleague is Jeff Lockmeyer. He's out here in the crowd, and he's our ground systems architecture lead. We'll get right to it. All right, so out at the Huntsville Operations Support Center, we're out in Huntsville, Alabama, and we have a 24/7 multi-mission facility that can deal with just about any type of satellite operations that we need to deal with. We're highly configurable. We provide secure and centralized gateway services and communications to a globally dispersed user community. All right, some of our heritage, some of the programs that we have been involved with over the years. Obviously, we go way back to the Apollo program. One of our first CubeSats was FastSat back in the day. Chandra, Skylab, Hubble, Lunar Rover. And where we're at today, we deal mainly with the International Space Station. That's on a 24/7 basis. Near-Earth Asteroid Scout, which is sitting upon Artemis 1 right now, ready to launch. We got the Solar Cruiser mission that's coming up. I'm currently the lead for that one. We've got the commercial crew program that's going on. We've got a multi-program project control rooms that are very configurable for different types of operations. And of course, we've got the Space Launch System Artemis control room in there for the spy folks. There we go. So the unit that I belong to out here is called PMOD, the Payload Missions and Operations Division. When you bring in your satellite program or project to us, you get assigned an ops director as myself, and we'll lead the integration and execution process to get you going and get your mission up and running. Let's see. We'll provide flight controllers. We'll provide that those flight controllers will execute the spacecraft our contacts, perform commanding, respond to anomalies. They'll also lead and coordinate mission planning processes for you. They'll build and validate the sequences, and then we'll also provide a ground systems lead, like my colleague earlier I mentioned, and they'll ensure that the HOSC is designed to meet your needs and your science needs. Sorry. So everything is hosted at the Mission Operations Center, and there's, like I said, those configurable control rooms earlier. There's various Mission Operations Centers within the HOSC. So we have the responsibility for development, installation, integration, testing, and maintenance of the MOC, and for coordinating and interface testing and data flows with the ground networks. Example, one of our sister units out there at JPL, we deal with the DSN quite often. We deal with the NEN, TDRS, and a few others that are out there. We do provide a ground system software solution for you guys, the Telescience Resource Kit, or TREC as it's commonly known. It's a ground system software used for flight operations and execution within one of our MOCs. Okay, so let's get over to the two main missions that we came here to talk about today. So Near-Earth Asteroid Scout and the Solar Cruiser. So the Near-Earth Asteroid Scout is a joint venture between us and JPL, and we propose to design, develop, and fly a controllable solar sail spacecraft. We want to get close to a near-Earth asteroid scout. It's pretty much what this is saying within probably around the 2-year point of our mission. The goal is to develop a capability that can retire strategic knowledge gaps. So senior leaders and leaders from our division, we get together and we figure out where are we missing. You know, where are we coming up short in certain areas. So this is going to close some of those areas. Characterization of the sail will be achieved using the 6U CubeSat, equipped with an imager. To perform the asteroid flyby, like I mentioned, and then we're going to get probably close to around less than 1 kilometer. To manage the potential launch slips, which those we know with Artemis, we've had quite a few slips. We do have a variety of potential NEA targets that we can choose from. We do have to go back and reestablish mission design properties in that to deal with each one of those targets. All right. It is a secondary payload, like I mentioned, on the Artemis 1 mission, and down at Kennedy. We're there with a whole bunch of other 6U CubeSats, and then we're ready, like I said, they're on the pad ready to go, and we're ready to go at Marshall, waiting for this one to go up. On the Solar Cruiser side, this is an 11-month mission, and the one thing I didn't mention about NEA Scout's got a 85 meter squared solar sail. Solar Cruiser's got a 1,600 meter square solar sail to it. This one's on an 11-month mission, and this one's more of a tech demo than it is an actual mission to meet with an asteroid. So this is a tech demo. So we're going to go up there and on the Grange 1 area, and we're going to do little roll controls. We're going to do attitude controls, just using the solar sail itself, that and micro thrusters. So this mission, we're going to be part of the IMAP program, and then we're going to launch around February 25. After the injection, we're going to do a checkout phase, make sure everything's up and running. Make sure all our systems are operational. We'll deploy the sail. We'll move to a sub, Sun Earth L1, to demonstrate maintenance of a halo orbit. Just cruise around a little bit. Once the halo orbit is demonstrated to be stable and sustainable, then we'll move on to our next phases. Exercise a few more capabilities that we have, as you can see written there. And then throughout this process, we'll be getting the data down, the technology development data coming down. And we'll process that and make sure that gets disseminated to the right engineers and science leads. Okay, how are the tail of the tape? How are they different? How are they the same? So the similarities are pretty much that 24/7 ops out of Huntsville to support configurable control rooms, the command and telemetry processing, the dissemination and storage. We provide the flight controller training. We provide the flight controller teams for the perform the mix and execution, and of course the solar sail propulsion concept. The guidance control is out of Marshall, and they do all the sail characterization for us out there. Some of the big differences. Well, one is the duration of each mission. We get a 2.5-year mission versus 11-month mission. NEA Scout was designed as a joint operation between us and JPL. So we use their ground system, we use their mission design and navigation, and we use their science objectives. That's a little bit larger team. It's a 5-member flight control team. But what we plan on doing during the final 6 months of the mission is demonstrating a downlink automation type activity. And that'll come into play in the Solar Cruiser side of the house. So like I said, Solar Cruiser is an 11-month mission. It's designed to be an independent mission utilizing Marshall resources. So we have a ground system locally, we have the mission design team locally, and the tech demo objectives were all designed locally. And that's a little bit smaller footprint, so that's about a 3-member flight control team because we plan on doing a little bit more automation with Solar Cruiser than we did with NEA Scout. And also one of the big differences is we're going to bring the command encryption requirements in and do that on the uplink paths of the house. All right. So where do we go from here, our mission enhancements? So we're going to continue to improve on the current established ground system architecture. From the software side of the house, we want a smaller footprint, and we're going to do that by containerization of tools and dependencies. We want to provide customized support to utilize microservices for rapid customer integration. We don't want to take 12 months to get you in the house and get you rolling. We want to do it rather quickly. Automation of the ground contacts, we kind of mentioned that a little bit earlier. This is through a project that we've got going on right now. It's called Automatic Spacelink Connectivity, or AutoCon. We'll demonstrate that on NeoScout during the final 6 months, and then we'll add that data to the Solar Cruiser for multiple mission phases of that mission. And then the last but not least, we want to develop the multi-mission flight controller. We don't want the stovepipe narrowed flight controller who only knows one mission. We want them to know multiple missions. So we plan on teaching them a baseline of knowledge at the Space Operations Academy that's located within our organization. That's a foundation knowledge that can be used on any mission. It's a smaller footprint of personnel to help you out, which overall reduce costs for the smaller missions. But they'll always have access to more individuals, and they always have access to more senior leaders to help them with those programs. And like I said, they can operate multiple missions, and then mission-specific training is the only delta for a flight controller, so that decreases their time that they have to spend in training. I believe that is it. Thank you for your time. If you have any questions. Yes, sir. No, it does not fit into a CubeSat. It's a little bit bigger. It's a small sat, so it's about less than 100 kilograms. Yeah, so it's a little bit bigger than that, but it does unfurl to about a third of the size of a football field. Mm-hmm. Any other questions? Thank you very much.
All right, thank you, Darren. Up next, we have Emily Walter from Morehead State University Space Science Center.
Hello, everyone. Can you all hear me good? Okay, awesome. So I am not Benjamin Malfris. I'm actually Emily Walter. Dr. Malfris unfortunately had a conflict, and so he was not able to attend the conference this year. But I am giving this presentation in his place, and I promise you, you are in good hands. So Lunar IceCube is set to launch on Artemis 1. It's part of the NASA Next Step program. We're one of the 10 CubeSats that are assembled into the SLS and waiting to launch sometime this year. Just give a brief overview of the project for those of you who may not be familiar with it. Lunar IceCube is a 6U CubeSat, and the goal is to observe water ice and other water-related volatiles on the moon. So we will be launching on the SLS, and we will be using a bit 3 ion thruster in order to achieve a low delta V trajectory that will get us to the moon in a weakly stable lunar orbit that will allow us to do observations with our IR spectrometer. Primarily, our mission is looking at movement of water volatiles and related volatiles on the lunar surface, as well as attempting to look at abundance of water volatiles near permanently shadowed regions towards the moon's poles. We also have a number of different tech demonstrations that we are a part of as Lunar IceCube, including our bit 3 ion thruster, our exact ADCS, and several others that are listed here. We have recently completed our operational readiness review as of this, a few weeks ago actually, and we are looking to launch with SLS, which is now scheduled for June of 2022. So just to give you a brief overview of the timeline of our project, we have a roughly 18-month mission timeline, and this is a little dependent upon launch date just because we are using a very low delta V trajectory in order to get to the moon. Essentially, we have about 7 days of LEOP before we do a lunar flyby that leads us to an Earth flyby, and then we transition into a cruise phase where we are both coasting using manifolds as well as thrusting occasionally. We will then be captured loosely using an NRHO, which will transition us into our spiral down, where we will stay for about 6 months where we're lowering our periapsis to get to our final science orbit. At that point, we will have a 3-month science orbit, or science mission phase nominally, with 3 months available for extended science depending on the availability of propellant. So in this talk, I'd like to give you an overview of all of our mission operations involving Lunar Ice Cube. So that goes through our planning, our mission operations architecture, and the preparation and testing that we've put into this system for verification once we get into flight. So to start, we are, as a 6U CubeSat, very limited in the amount of propellant that we can take with us, which limits the amount of delta V that we can use in order to get to our goal science orbit and positioning. So in order to maximize on the propellant that we do have, we're using what is essentially the interstellar highway, the interplanetary highway. That is a very low delta V, but sort of long and a bit convoluted pathway that we use to take advantage of gravity assists and Lagrangian points to get to our final orbit while not using as much delta V and propellant as would be needed for a larger mission with a direct transfer. And so this is an image of what our trajectory looks like. This changes a little bit based on launch date, but as you can see, we start with a flyby of the moon roughly 7 days post deployment. Then we thrust in our deterministic maneuver until we get back to the Earth, where we do a second flyby. We end up in cruise, where we're thrusting in between to ensure that we get our correct line up with the moon, and then we are captured in the NRHO, which is shown in the next slide. And so here you can see in red the sort of loosely bound, slightly chaotic looking NRHO that we end up in, and it leads to our periapsis lowering and spiral down phase, where we are in the correct plane using the correct beta angle, and we lower our periapsis routinely over this until we get to a roughly 100 kilometer periapsis that we'll use for our science observations. And so this is an example of what our science orbit looks like. We essentially are trying to be as near polar as possible, and we utilize a beta angle that allows us to ride the terminator of the moon so we can look at the transition from light to dark. We go from the South Pole to the North Pole at our periapsis so we can observe both of the poles with our IR spectrometer. And so we can look in the 1 to 4 micron range to look for different volatiles that are associated with water ice. Okay, so now that we're past the planning point, I'd like to give a brief overview of our mission architecture. I apologize that this slide is a bit of a eye chart, but we have a very complex architecture, but I'll try to break it down into the main piece parts of it. So we have our in-house Mission Operations Center, our MOC, that contains all of our archiving, all of our telemetry reduction and interpretation, all of our science data, initial storage, and any command generation that we need to do on our part. We connect with several other organizations through the MOC to take spacecraft data and give it to them and to receive relevant information for ourselves so we can use it for command generation and mission planning. We utilize the Deep Space Network in our communications since we are going beyond Earth orbit, and we also work in partner with Goddard Space Flight Center, where their flight dynamics facility handles our trajectories and our thrust maneuver planning. From our archives, we also have a number of subject matter experts at our various partners related to our subsystem development that we send information to in the case of critical events, events that may be relevant to their research, or in the chance of anomaly. If we have an anomalous behavior on the spacecraft, we send that to them for further diagnosis. And then we also have our Science Operations Center, where we send all of our raw science data, as well as relevant telemetry, so we can process that using our NAIF SPICE tools and our in-house reduction codes to get a level 0 through higher level data products. Okay, so this is a brief overview of how the data flows from a telemetry and command perspective inside of our Mission Operations Center. So because we're working with the Deep Space Network, we primarily utilize the SLE in order to communicate with the different DSN assets. So on our downlink path, we utilize CCSDS standard protocols such as AOS frame decoding to get our telemetry from the SLE gateway. And then we also use uplink CCSDS protocols, specifically forward CLTU, to send that data to the UPAs that are relevant DSN stations. So this whole section of the architecture acts as a transformer of sorts to get raw data from the spacecraft to a human readable form, and also to get human readable commands to what the spacecraft can inevitably understand. So along with all of this preparation and architecture development for our ground station, we also have done extensive testing with our ground station, specifically involving the DSN. Since we are using their assets, we both have to verify that we're able to connect and properly work with the SLE, and then we further vet that by testing our ground station and our ability to connect to the SLE against every DSN asset that we intend to use. So we have extensive testing that we've done both in a single spacecraft configuration with the DSN, as well as in multiple spacecraft per aperture, or MSPA, that we have utilized to show that in the case that there are several spacecraft that are within a beam width of a DSN asset, that we can all downlink at the same time, which helps with dealing with congestion in the DSN availability. So part of sort of the fortune that Lunar IceCube has had in our development is that located at Moorhead, actually co-located with our MOC, we have a DSN asset, and we're actually the first non-NASA node on the DSN, DSS-17. So DSS-17 is scheduled to support a number of the CubeSat missions that are going to the moon, as well as other missions. With DSS-17, we have a 21-meter dish that is DSN compatible, so we can use it for testing as well as proficiency tests. And as you're about to see, we have extensively tested it end-to-end with Lunar IceCube. So Lunar IceCube had end-to-end testing in which data was flown from the radio of Lunar IceCube through coax to horn antennas on top of our building, and then transmitted to DSS-17, where it was received and then put through all of the DSN back support of the antenna. Oh. And so in this end-to-end testing, we both got to vet and prove out the capabilities of DSS-17, as well as get to do some extensive testing with our spacecraft to prove that things are working correctly and that our ground station is properly interpreting all of our information. So along with this testing with the DSN, we've also included testing with our flight dynamics facility, specifically from an operational readiness training point of view. So in this, what we have done is we've essentially taken our relevant engineers, all of the engineers who are acting as flight operators, as well as our FDF partners, and we have sat down and done real-time equivalent testing of critical maneuvers that occur early in the Lunar IceCube mission plan. So pre-lunar flyby, we have to do things such as a calibration burn and a deterministic maneuver with bit 3 in order to make sure that we properly hit our lunar flyby and we don't go heliocentric. So in that, we have sat with FDF and ran through all of these in real time with our FlatSat, just to vet that all of the processes involved in our command generation and communication between both groups is in place, and that we are properly trained and ready to support the mission. So, moving forward with the mission, we have a number of things that we're focused on. We're continuing to do FDF sims. We worked through our calibration maneuver as well as our first deterministic maneuver, but there are several other critical events throughout the life cycle of the mission that we would like to also go through with FDF. Along with this, we have operational readiness training just for the flight operators. Essentially, once we are within a certain time period of launch, every 2 weeks we will begin to do regular training just to keep everyone up to date with our procedures, with the flow of activities, and everything necessary for our mission. We have passed our operational readiness review, and so we are just preparing now for launch of Artemis 1. And so we are ready. So are there any questions? Yep.
Yeah, how much time after the release from the SLS before you first use the bit 3?
We will first use the bit 3, I think within a day, because we have to do our calibration maneuver. So all of the calibration maneuver and the first deterministic thrust maneuver occur in the first week after deployment. So essentially, with a small sat, you think that everything is smaller. However, because of the limited space, limited propellant, limited power that you're working with, you actually really heavily constrain yourself in a lot of ways. And so complexity grows in a lot of areas where you have to deal with these physical constraints. So, for example, when you're dealing with the physical constraint of propellant, you have to take this more complex thrust maneuver in order to get to your target instead of doing something simple like a Hallman transfer. Or in the case of software, because our spacecraft has to do all of these complex things to make up for what it lacks in available mass and available propellant, our software has to have a much higher complexity than you would expect for a small mission. So it's just part of doing big things in a small container. Yep. Any others? Yep.
What did you finally do for heat dissipation?
For heat dissipation, we specifically with the birches, because where we're running an IR spectrometer, we have to have active cooling. What we ended up doing was installing a deployable radiator on that part of the spacecraft, and so that was that allowed us to get to the temperatures that we needed to during our thermal vac testing. Anything else? Okay. All right. Am I good to? Okay.
Okay, thank you, Emily. Up next, I would like to welcome Matteo Capella from Leith Space.
Okay, can you hear me well? Yes. Okay, good afternoon, everyone. Thank you for being here. My name is Matteo Capella, as already been introduced. I work at Leith Space as regulatory affairs specialist. Live Space, for those that don't know us, is a ground segment as a service provider. We have about 15 stations around the world, supporting currently 60 satellites in LEO. We will have our CSO talking later today about the company, so I'm not going to talk too much about it. We are here today. I'm here today because I would like to talk about the importance for satellite operators to consider ground station licensing or their process. We will see a bit of the type of licensing and why it's important for the satellite operators to think about their station licensing as well. I will introduce a bit the general framework that one can expect when we're trying to request for an air station license around the world. And then we will go through some issues that we have met whilst working around the world with different regulators and what we see. And usually this is reflected and issues come up because of something that has been done on the satellite operator side in their own ITU filing. So this is also why it's important that you consider ground stations licensing from the beginning for your mission. So general type of licensing, we are all probably familiar with what kind of licenses we need during for a space mission. I will focus on the second bullet point, so the Earth stations or radio communication licenses, they have different names around the world. This is important, as I was mentioning, because often it's much better to plan in advance. It's less costly to plan in advance compared to fixing it later during the process, because there is a lot of steps that might be involved with us having to go back to you and then we're dealing with regulators or potential certified persons. You don't want your satellite to be stuck in LEO with less than optimal number of ground stations because of bureaucratic reasons. So it's important to move way in advance for this. And also this is important for satellite operators because sometimes there might be work that needs to be done on your side to operate in a specific country, even if then the license from the ground station is actually on our side to be taken. So the general framework for an air station licensing, it's usually involves 4 elements, which is a single point of interface. So usually a regulator that then might deal with others in the country. So FCC in the US that then deals with NTIA and other federal actors, or radio spectrum management in New Zealand, or Ofcom in the UK, and then they go back to relating also with others within the nation, which means that this can add some steps that you might not see, but that add time from when we ask for a ground station license to when you actually go and receive the authorization to operate. Usually there is a form to fill or some procedures to go through. Those are the details that are usually asked, so details on the ground station side, center frequencies, the ITU filing that for the satellite that we will communicate with. And so, as you can see, it's very important that you already have an ITU filing when you come to us and ask for a ground station. This is not often the case, and this can add delay because we won't be able to obtain a ground station license until your ITU filing is actually available on the ITU website. Sometimes you might be asked for assurances as satellite operators, so letters and letter of assurances that, well, you commit to respecting specific regulations. And sometimes there are also intermediaries and certified engineers, for instance, that are required by law to be the point of contact between you and the regulator. And this is the case of New Zealand or Australia, which means that this adds an additional step to obtain an air station license. And so, again, going to a ground segment operator 1 month from launch doesn't necessarily ensure that you will be able to lawfully operate from a ground station that they have. So now I will go through 4 common issues that we met. They are usually related to what is in the satellite ITU filing or what it is not on a satellite ITU filing, because this is often done maybe by the satellite operator without considering what kind of ground stations they will use in the future. So some data might be mismatching, for instance, with what the ground station can actually do. The first issue usually that we met, it's not being able to get an air station license, or maybe getting it with significant delay based on the ITU filing status, the satellite ITU filing status. So with status, I mean at what point of the ITU process the satellite filing is, which could be either just present on the ITU website, and so this is called as received, or officially acknowledged by the ITU, so published in an International Frequency Information Circular, IFIC, which is a bi-monthly publication that the ITU publishes, where it officially acknowledges what kind of satellite filing they have received. Or there could be the final notification of a satellite, which is the moment where you actually secure your frequencies and you gain the right to ask for protection from interferences. And so when the satellite finding is just as received, most of the ground stations that we use and most of the countries where we operate will be fine in releasing an Earth station license, maybe with some assurances. But some countries might instead prefer to just release a temporary license or wait for the filing to actually be published in an IFIC, which means, for instance, that if you want to use a ground station in New Zealand, your satellite is close to launch or already in orbit, but your satellite filing is just as received, you will have to wait until the filing is actually published in an IFIC before being able to operate lawfully from New Zealand. And again, we had situations where satellites launched could not use the ground station in New Zealand because of this, and it's not nice when you are relying on as many stations as possible for LEOP and you can't actually operate from some of the stations. When the filing is published in an IFIC, you might still have regulators asking you for letters of assurance because you have not fully notified your satellite. And so this might mean, again, back and forth between us, between the regulator and you to make sure that you nail down the right wording for an assurance letter. And then this needs to be approved by the regulator, and then only then we get an Earth station license. The second issue I would like to talk about is the lack of a country within the satellite service area. This is a screenshot from the ITU software SpaceCap, and I highlighted there the service area, which is the list of countries where from you are operating your satellite, or where we are operating your satellite from. You can specify in your ITU filing the list of countries where you will have ground stations or where you will be downlinking if you're broadcasting, for instance, in a country. And this can be generic, so you could include international coverage, but this will increase, of course, the number of coordination efforts that you will have to make. Or you can actually specify the specific countries that you will operate from or where you will have your ground stations. Some countries will not release an Earth station unless their country is present in your service area. So knowing this in advance can make sure that you are not surprised when from the list of the ground stations that the ground segment provider gives you, then you're not able actually to operate from all the countries because some of them might ask you to go back to the ITU and add their country in your filing. And this, again, is an example from Australia where they want you to have either global coverage or Australia as a country in the service area. The third issue is the associated Earth station. Again, every ITU filing, this is again from the software SpaceCap from the ITU, you should point out the characteristics and where the ground stations that you will use are located. You can either have generic ground stations, so without an actual location, but indicating already the kind of gain that the ground station might have, or the kind of beam width that the ground station might have. Or you can specify the actual coordinates of it. And some countries, even if you have the country in your service area, might not give you a license if the license actually doesn't, if your ITU filing doesn't actually include specific ground station within their country territories. And this is, again, is an example of Australia, where they want to make sure that that the ground stations you're operating with are present in your filing. And sometimes you might have a ground station within a country, but the characteristics of the ground station might not match the characteristics that, for instance, we have in our actual physical ground station, meaning if a difference of gain might then come back to us as the regulator telling us we can operate only with a reduced power of transmission because it doesn't match the gain or the overall transmission power that you indicated in your filing. The final issue that I want to talk about is the mission characteristics that are, again, in the ITU filing of a satellite. And this, again, is a screenshot from the software. Usually, and it should be present, it is present in ITU filing, and it describes actually the transmission characteristics for the uplink. So it relates to the Earth station operation characteristics rather than the satellite itself. And so it's important that you go to ground segment operators, if you want to use third-party ground segment, to actually ask them what kind of power they are able to do, what kind of power, what kind of data you should put in your filing to make sure that this matches the ground stations that you will be using. Because again, you might have regulators asking you to match or asking us to match the characteristics that the satellite operator have introduced in the ITU filing. And if these are not, there is no match, we might be asked either to operate with lower power transmissions or simply not be able to receive an authorization until you go back to the ITU and edit your ITU filing. So some final considerations. Again, it's important to consider the Earth station deployment early in the process and the licensing early in the process, because as mentioned before, sometimes it's easier and less costly to plan in advance compared to go back and fixing things. Ground segment providers as leave space, but anyone, honestly, we are very happy to talk to you in advance, support you in your ITU filing to make sure that it matches the ground stations that you will be using afterwards. And the final point, which is the most important, is that behind the forms, behind the procedures and all the licensing processes, there are people. Most of them might not be familiar with the space sector and the trends and how fast we have been starting moving in recent years. They must have had a surge of space activities and space licenses requests, thanks to transporter missions, for instance, that imply waves of Earth station licenses arriving at regulatory offices every other month. And they might want to listen, meaning that they might want to might want to hear and then able to change their procedures based on the actual needs of satellite operators. So this is a very important point to keep in mind. This is all on my side. I'm very happy to keep hearing from you, and if you have any questions, I'm open right now to try to answer, or we have the booth upstairs, so I will be here also tomorrow if you have any question. Okay. Thank you. Thank you very much.
Okay, thank you, Matteo. Up next, I would like to welcome David Besson and Brian Gunter from Amazon Web Services, Aerospace and Satellite Professional Services.
Thank you.
Hello. Thanks for having us. I'm Brian Gunter. This is David Besson. We are aerospace cloud consultants with Amazon Web Services. AWS has been providing highly scalable, highly available, and highly secure computing solutions since 2006. We provide compute, networking, database, storage, a host of other services, AI, ML, IoT. We provide these all at a massive scale. We support workloads from anywhere from scrappy startups all the way up to Netflix. So in order to facilitate all these workloads, we love to innovate. We love to create new services. For example, in the year 2021 alone, we created 3,084 new major capabilities and added those to the AWS ecosystem. So the reason we're here today is we want to go over one of these new services, and that's AWS Ground Station. AWS Ground Station is it's a fully managed service. It allows you to communicate with your satellites. It allows you to rapidly deploy and scale your operations, all without having to manage the underlying networking infrastructure and the actual hardware. You get to offload the complexity and the cost of managing all of your antennas. So one of our early adopters to this service is Capella Space. They're all in on AWS. They're using our AWS Ground Station service to leverage a network of antennas all around the world. They are able to ingest data for their Earth observation solution, process the data, and then provide this data to their customers all in a matter of minutes from ingestion. We're super happy to have Capella on board. So what we want to do here, David and I we're both from AWS Professional Services, so we help people come onto the cloud. What we want to do today is provide a proof of concept. So what we're going to display today is we're going to acquire imagery data from the NASA JPSS constellation. We're going to process that data to provide these lovely images that you see here. And then on top of that, we're also going to expose data and metrics coming from the AWS antennas. And we're going to expose this through the Amazon Managed Grafana front-end service. So without further ado, I'll turn things over to David here. He was awesome enough to put all this together for us. So thanks, David.
Okay. Thanks, Brian. And again, thank you for having us. It's really exciting to be here. It's my first time. I've had great conversations already, meeting a lot of you and learning about your work. So thanks for having us. So what we're going to switch to now is showing how Brian and I have really cool jobs, and we get to apply these existing AWS services for aerospace specific problems. So we're paid to come in and develop projects for customers and show them how these services can be architected to create solutions that benefit their program, company, academic institution, whatever the case is. So what we're showing here with the concept of a reference architecture is just a starting point. This is, again, a proof of concept solution that shows how these services can be applied to do a space-specific problem. So again, starting on the bottom, kind of the phases of what we're talking about: acquisition, processing, and distribution. So those are sort of the general terms we'll be using. And then the services that do the heavy lifting to accomplish that is the AWS Ground Station service, which we'll dig into in a little bit. The EC2 service, which does a lot of our workhorse computation for a lot of different types of cloud architectures. We use the Simple Storage service, which is a very easy to use, cost-effective way to store massive amounts of data. And then we visualize it using Amazon Managed Grafana service, which is a deployment we do of an open source tool called Grafana, which you can use for dashboards. So the goal of this presentation today is to give you all a little bit more intuition for these relationships and how you can start tying services together to make overall solutions to solve your technical or business needs. Something that I don't know that's been talked about too much in the conference so far is the idea of infrastructure as code, which is something that Brian and I do for our projects. So this is essentially just creating a script file with a kind of paper version of the cloud architecture you're going to deploy, but it follows a very specific schema structure so that the Amazon services that interpret it know how to deploy what you're asking it to do and simplify the hands-on work that you need to do if you're trying to do this step by step. So there's a blog post that we're going to link to at the end of the presentation that has a lot of documentation about this specific cloud formation template we're using. If you want to dig more into that, but just again, at an intuitive level, what's happening is you start with a JSON or a YAML file, just a script with information about your cloud architecture. You feed that into the CloudFormation service. It deploys a stack on your behalf, and then within that stack are the actual services. So just running through these quickly, again, AWS Ground Station, this is how you do the space-to-ground connection with the antennas that we own and operate. Simple notification service, this lets you send emails and text messages, but not spam. We're very serious about this. There's a lot of protections in place to stop that. EC2, we've talked about. Lambda, probably my favorite service I work with day to day. This is how you can basically take a Python function and put it on the internet and actually, interact with other AWS services and external data sources with it. I use it constantly. S3 we've talked about, and then CloudWatch is a way to aggregate the logs that are produced as your architecture is working, and you can also do some automation events with it as well. This is a kind of unique slide talking about Ground Station because it's a unique service. However, the point we're trying to get across is that you're using it sort of just as if it's another cloud service. You interact with it via APIs. There's pay-as-you-go pricing. You can interact and interface with other services, and it's just a very clean way to interact with spacecraft. That's not to say you have to use this if you're doing space-based architectures with AWS, but it is something we provide now to help accomplish that. And right now we have S-band and X-band links. So now getting into processing the data. So the way that this works once you've deployed the architecture with your CloudFormation template is that you reserve a contact with Ground Station. When the satellite is overhead, the downlink occurs, and in this example, we're using a NASA satellite, JPSS-1, which is in a sun-synchronous orbit. It's like 860-kilometer altitude, ingest the raw data, do the demodulation and decoding. That creates a set of raw data files. Those go into the S3 bucket. And then this is where like the real power of AWS comes into play with the automation. So you don't have to do anything else at this point. A bunch of automated triggers take over and push the data into the EC2 instances. Think these like virtual machines, you know, like desktops, not really desktops, but computers in the cloud that are configured in a specific way to process this data. So there are two that we're running using NASA open source processing software. One kind of acts as the receiver, which bundles the raw data files into a level 0 imagery data product. And then that goes into the processor instance. And that takes the level 0 data and turns it into actual like human readable images, the level 2 data. And there's a lot of great NASA documentation about how they do this on the NASA Data Readout Laboratory, which is also referenced in the blog post that we'll get to. And when it's finished, you get an email notification. It's all automated again, and it tells you that the processing is finished. It gives you some high-level metadata about what was done, and then you know that you can go into the S3 bucket to check it out. And so the blog post ends here. So the new stuff we're adding is special for you all here at the CubeSat Developers Workshop. So what we do next is we take those data sources within Amazon, and we start combining them into a dashboard that's much more human readable, more intuitive, a way to share with your team or even external end users what's going on. And as Brian mentioned, security, you know, job 0, top priority with us. So the way that you can protect this for the actual working data is through AWS single sign-on. So you've probably encountered this or something similar as you've worked with different web applications, but this tightly controls who can access the data itself and the dashboard and what credentials are needed to do it. From there, it goes into the managed service for Grafana. Again, open source dashboard technology. You can download it for free on the internet. But this is a special Amazon version that streamlines the connectivity with the other Amazon services. And so the data sources that it's pulling from, CloudWatch. So this is giving a very clean interface into the metrics that were gathered while the architecture was running and processing the downlinked space data. And so on the next slide, I think when I show the signal to noise metrics for ground station, it comes from CloudWatch. And it's very easy to access this, again, via APIs and automation within your architecture. There's some other metrics, too, that we'll talk about. There's another service called Amazon TimeStream. This simplifies the way of managing data that comes from Internet of Things devices or things that are just natively time series dependent, so that you don't need to worry about dealing with a relational database or NoSQL. Maybe I'm getting a little in the weeds here, but it's a great service and has very clean integration with Grafana. And then again, S3. But the other special thing we're doing here that may be unique for the types of things that come up at this conference is the idea of a pre-signed URL. So when you're actually trying to get the data you've worked so hard for with your CubeSat mission to your end users or customers, you have to protect it so that it's not downloaded, a million times, or you want to control who's able to download what. And we have very, again, clean methodologies for doing this with the simple storage service. So in the example on the next slide, the URLs that are in the bottom right are these sort of protected access points for downloading the data. So this is what we're building towards, again, and maybe a little hard to read with the specific tab titles, but we do have a QR code on the next slide if you want to pull this up and see a kind of simplified version, just how the data flow looks. But really the big takeaway of this session is that on this slide, what you're seeing is like the macro scale data engineering for a space mission. So on the top left, you have the ground station signal to noise metric. So this is raw RF data coming from space, and you're picking out that metric from the ground station terminal. In this example, we're using the one in Oregon. Going one level down, that's the network traffic going into the receiver EC2 instance, so a scale of gigabytes. So you're watching this like sequentially, right? It's like a cascade of you go physical layer, raw data going into the instance. The third from the top, that's CPU utilization. So now the processor instance is actually turning the crank, and you're watching this happen as it digests it. And then finally, the network traffic out of the instance, where it sends the processed images back to the S3 bucket. And then on the right, these are more systems engineering level KPI type information. What was the, I think, average signal to noise for the downlink? What was the max CPU utilization to help you estimate if you need to change sizes of the processors? The types of images that were downloaded, total quantity of data, and then some other kind of aggregated metrics about what was downlinked. And then finally on the bottom right, these are URLs you can click to download the images that you saw at the beginning of the presentation. So these can range from 30 megabytes to 500 megabytes. They're TIFF files, but there's, again, NASA documentation for how you can incorporate these into your geospatial visualization suite of choice. So with that, if anyone's interested, including folks online, this should work through magic of the internet. You can scan the QR code and you'll see the simple version of what I just presented on the previous slide. It is not optimized for mobile, so if you want to send it to yourself to look on your computer later, that might help as well. And this will be up for about 24 hours. So it won't be there forever, but if you are curious about seeing it again or have questions, you can email us and we're happy to do some initial proof of concept demos. We'll go from there. So hopefully I've given enough time for this. And what I want to end with is another really cool quote from NASA. I'm not going to read it, but the idea is, again, with these reference architectures, it's the baseline and foundation. From there, you can add things in a number of other directions. So if you want to add machine learning for image recognition of the objects in the S3 bucket, we have workflows to do that. If you want to add Alexa for some reason, to be like, hey, how many images did I download? Like, we could do that. Storage to like the heat death of the universe. Like, can't actually do that, but we're pretty close. And just deep archive, store it forever. There's a ton of different directions you can go. And so that's kind of what NASA was getting at here with this other project we did a few years ago for general data distribution for some of their data products. So again, thank you for having us. Cubesats are super cool. I would like to work with them more. We are, spread a little thin with the different projects we're working, but if you have any questions, follow-up ideas, feel free to reach out. Our emails are there, or if you see us, we're happy to give you cards. And then there's one more QR code here, and that's the blog post I mentioned that goes into full detail for how the NASA software is configured within the architecture and other things. So yeah, thank you. Really appreciate the opportunity. So.
We're also happy to take any questions, so if you have any.
The physical link between the satellite and like the antenna. So it's managed via a mission profile that you configure when you set up the ground station service. So like I mentioned, the like YAML and JSON stuff, there's like a subset of that applied to the link itself. So that gets into like which frequencies you're using, which modulation scheme, bandwidth, things like that. And so there is an RF compatibility assessment phase we go through. You don't need to do that for this example because they're the NASA public broadcast satellites. But there's a similar infrastructure as code type setup before you're able to contact.
And I'll add to that, if you're asking about the physical, like how do we connect the antennas to the AWS network, we actually co-locate these antennas with our data centers. When possible. We have one exception where one antenna site's in Hawaii and it kind of reports to the Oregon region. But in general, we try to keep them like co-located with AWS regions. And so they inherit all the top security controls, encryption, all the massive bandwidths that the AWS network provides. So. Right now, so the question was how many ground stations do we have? So right now we have, I believe we have 9 fully functional regions. This is a new service, so we're adding things pretty aggressively right now. We have 9 that are fully available for general use, and we have another in South America right now that's in preview mode. Hopefully it should be in general availability very soon. So and we're always adding more. AWS infrastructure in general, regions, data centers, and our ground station antennas will follow the same paradigm. Yes, I can't comment on specifically what we are adding next. We're customer obsessed. We always listen to our customers, like what bands do we is there the most need for. Right now we have S-band available for up and down and X-band for down, and we are in the process of reviewing customer needs and adding bands in the future.
I think we may be out of time, but again, happy to answer more questions offline. Emails are up there, so also the emails are embedded in the dashboard demo. So
yeah, and we'll
trying to cover all our bases here.
We'll be wandering around today and tomorrow too, so just grab us. So,
all right, thank you.
Good job.
Okay, thank you very much, David and Brian. Up next, we have Susan Tower from MMA Design, LLC.
Good afternoon. I'm Susan Tower. I'm a principal mechanical engineer at MMA Design. And today I'll be presenting two of our CubeSat antennas that we've been developing over the last couple of years. First, I'd like to go over a bit of our background in membrane-based deployables. We utilize membranes in many antenna applications. Passive, which is a reflect array, and one of the antennas I'll be presenting, our T-Dagger, is a passive antenna. Our active antennas, we've been developing Yagi, log periodic, spiral, phased array, and I'll be talking about the sinuous lambda antenna as well. Dipole and helical. We've been developing membrane-based antenna technology since 2013, and we have used flight-proven materials and have reduced our risk that way for stowage and deployment, environmental protection, manufacturing, and system architecture optimization. So T-Dagger is our high-frequency antenna. It was chosen as a payload on the Maxwell mission. It's for the University of Colorado team on a 6U bus, and it's a demonstration of the T-Dagger X-band operation. It's a technology demonstrator for future deep space communications, and we would like to thank the AFRL and the University Nanosat program for their sponsorship in this program, and is expected to deliver in the next couple of months. The attributes of the antenna, it's a Cassegrain configuration. It has 4 independent primary reflect array facets and 1 subreflector. It contains 8 fiber-reinforced polymer tape spring booms as structural elements. It's a 0.7 diameter aperture. It can stow in a 1U stowed volume, but for this particular mission, they asked for some extra features, and so it's actually in a 2U system. 1.3 kilograms, 29 dBi at 8.4 gigahertz for the flight unit, and a bandwidth greater than 25% for X-band. We have tested this antenna at the range. Testing was done at 9 gigahertz in conjunction with some other developments we were working on with another antenna. We did the RF verification this way for bandwidth, collimation, and pattern shapes, and compared those to the simulations and made sure everything was going the way we wanted it to. Future testing will include the 8.4 gigahertz version of the membranes. The mechanical design leverages our high TRL enabling technologies. It requires an innovative deployment and a mechanism designed to fit in the small 1U size. As I said before, there are 8 composite tape booms. A single motor drives a drivetrain which synchronizes the deployment of the 8 booms. The membrane uses an origami-inspired folding strategy, and the membranes also act as a structural element. They help stabilize the booms themselves. And here's a deployment video. The current status of this development is currently undergoing environmental testing. We have completed system tuning, vibration testing, and we have range testing and thermal cycling remaining, although at this point today it might already be done. And the flight unit, as I said before, we expect to deliver in the next couple of months. The second antenna I'd like to talk about is a lower frequency 1 meter antenna. We call it Lambda. This antenna is being developed for the NASA Snoopy mission in cooperation with Purdue University. This antenna stows in a 1U by 1U by 2U volume and has a two-directional deployment. There's a truss boom that does the first deployment, and then a shearless boom does the second deployment direction. And the antenna performance, the gain is greater than -1 dBi. The beam width is 50 degrees. The frequency range is 137 to 380 megahertz, but this artwork can be changed to work up to 1 gigahertz. The VISWAR is greater than 2 to 1, and the polarization is dual circular polarization. This antenna is dual directional. The truss boom is made of fiberglass, which enables dual direction. It is 1.5 meter long and made of 3 high-strain composite slit tubes. The 3 tapes are deployed by 1 motor and a central gear. The truss boom has 9 bays. They are connected with a fiberglass cordage. And the middle bay, the fixed bay, contains the lateral deployer of the shearless boom. And we've tested this boom to a fundamental frequency of 3.1 hertz. The fiberglass shearless boom, this is a development that we've licensed from NASA LARC. The shearless boom is a sheath-based, rollable, lenticular-shaped, and low-stiction boom. That is, it's 2 tape springs oriented in a lenticular configuration and bound together with a polymer sheath. We developed a yin-yang stowage concept, and it's self-deploying. There's no motor. And so this is the stow configuration with a membrane, and then we deployed it with the membrane. So this is a video of the truss boom. It takes about 15 minutes to deploy this, and I sped it up to 30 seconds. And this is a video of our self-deploying shearless boom. Our next steps are to integrate the 2 subassemblies with the membrane and do a fully integrated demonstration of the deployment. Upon funding for flight, we'll complete a EQM and complete qual testing and build the flight units and get these flown. Thank you. And just like Moog, we're hiring as well. And I'd like to thank my colleague, Colin Peter. He did most of the development work on the T-Dagger antenna. Any questions? Yes. Which frequency? I'm a mechanical. I'll have to ask the RF engineer who designed all of this, but sure, why not? There's probably a little magic box in there that figures that out. Call us and we can tell you. Any other questions? I don't see. All right, thank you.
Okay, thank you very much, Susan. In just a minute here, we are going to welcome Hana Tomio from Massachusetts Institute of Technology.
Hi, so I'm Hana. I'm a graduate student at the Space Telecommunications, Astronomy, and Radiation, or STAR Lab at MIT. Today I'm going to be talking about the CubeSat Laser Infrared Crosslink, or CLIC mission. This is a joint collaborative project between my lab, under Dr. Carrie Cahoy, the University of Florida Precision Space Systems Lab under Dr. John Conklin, NASA Ames Research Center, and Crosstrack Engineering. So the focus of my talk is going to be on the development and testing of the optical transceiver for the second stage of the CLIC mission, but I'm also going to take this opportunity to talk about the mission as a whole and give an update on its current status. So laser or optical communication technologies have numerous advantages and avoid some of the disadvantages of traditional RF systems. So the higher directionality and narrow beam width means you can have a smaller, lighter, less power-intensive terminal while achieving some pretty high data rates. And that's particularly relevant for small satellites because of their size, weight, and power, or SWaP constraints. Some particular applications include high data rate crosslinks for constellations, which is a pretty popular mission paradigm these days. Think like global connectivity, OneWeb, and Starlink. And we can also do precision ranging and time transfer for scientific applications like interferometry. So the goal of CLIC is to develop these miniaturized optical transceivers compatible with CubeSat SWaP constraints using commercially available off-the-shelf components, in addition to having those communication capability, also be able to do ranging and time transfer. So CLIC is a two-phase mission involving three 3U CubeSats. Each CLIC payload, which is just the optical transceiver, is going to be integrated with a bus system from Blue Canyon Technologies. And all three CubeSats will be launched to low Earth orbit in the 2022-2023 timeframe. We also have a parallel optical ground station development effort that's called the Portable Telescope for Lasercom, or PORTEL, and that's going to be our primary optical ground station for CLIC. So the first CubeSat, or CLIC-A, is going to demonstrate just the downlink capability, and so that's sort of serving as a risk reduction mission for us to validate the design of the transceiver, particularly the fine pointing system, the operation of the optical ground station, and the mission success criteria for that is just greater than 10 megabits per second. Following CLIC-A, we'll launch two CubeSats, CLIC-B and CLIC-C. They'll be capable of not just downlink, but also the crosslink capability. And their mission success criteria is greater than 20 megabits per second for the full duplex crosslink, and a ranging accuracy of better than 0.5 meter. And that's over a full demonstration range of 25 kilometers to 580 kilometers, though we also hope to do up to like 850. So this shows the mission concept of operations for CLIC-BC. Sort of common with both CLIC-A, what's really key to the CLIC mission is our two-stage beacon-based pointing acquisition and tracking sequence to establish the communications link. So for CLIC-B and C in particular, First, the two CubeSats will perform differential drag maneuvers to establish the desired separation distance. Then they're going to establish an RF crosslink, which will be used to exchange real-time GPS ephemeris data, and that's sort of an open loop, very coarse pointing. After that, both payloads will transmit a 976 nanometer beacon laser, which will be used to sort of establish a closed loop, more fine pointing system, following which we can transmit the actual C-band communications laser. And so, as I mentioned before, there'll also be downlink tests with each of the CubeSats. So this shows the Click BC payload. It leverages a lot of the heritage design from Click A, but the three sort of main systems are, let's see, trying to find oh, there we go, are the optical bench, which is shown here on the right, that has the transmit and receive paths, as well as our pointing acquisition tracking, our PAT system, which is really based on the use of this MEMS FSM. That's a fast steering mirror. And that's located above the fiber raceway down here. And then all of the electronics boards, that stack is in the rear of the payload, sort of opposite the aperture. And we also have this thing sticking out here. That's a chip scale atomic clock, which is used as the reference for arranging and time transfer. This shows the optomechanical design in more detail. So as I mentioned, at the start of the CONOPS, we transmit this beacon signal shown right here. That's a separate aperture from the transmit, so it's fixed to the actual payload structure and pointed using the body pointing of the spacecraft. On the other side, on the other payload, you'll be receiving that signal through this beacon tracking camera. And so we do some image processing to get feedback that's transferred to the bus ADCS system in order to perform the body pointing. That beacon signal is also simultaneously received over here on this telescope, and it's routed with the FSM reflected off this dichroic to a quad cell, a quadrant photodiode. And so this signal is used as feedback to steer the MEMS FSM. And then once we've established that and centered that signal on the quad cell, we can transmit here. So yeah, because they shared sort of the same optical path, by manipulating the FSM, we can align the transmit and the receive in the beacon signals. And that receive path is then sort of routed down to the APD here. And I think I might have said the Click BC payloads are identical. That's not quite true. They actually use two different wavelengths, B and C, in order to enable some spectral isolation for the full duplex operation. So the dichroics, like what passes what wavelength, is flipped between the two payloads. So for both or all Click A, B, and C, we use pulse position modulation. And on BC in particular, we're doing that with a semiconductor optical amplifier, or SOA, which is just acting as a shutter. This is sort of optimized for PPM, which, if you're not familiar, essentially you have a single laser pulse and you're dividing up a specific time period into different slots of a sort of predetermined period. And so what pulse or what slot the pulse rising edge appears in tells you a symbol, basically. So for example here, this is like 4 ppm, ppm4. You have 4 slots corresponding to being able to transmit like 2 bits. And so then you have basically, like, as you increase your ppm order and the number of slots, you're decreasing the duty cycle, but increasing like the number of bits you can transmit. So currently on Click BC, we're in the midst of testing. We've sort of finished the initial revisions of our boards and procured a lot of the optoelectronics components. We've set up this flat-sat test bed specifically for testing. And so this shows some of that initial results confirming the transmitter average output power and modulation. So this is taken right at the output of the SOA. And basically, as we expect, the average output power is proportional to the duty cycle divided with each increase in ppm order. So the expected measurement is shown in orange, and we can see our measurements sort of track pretty well with that, though some efficiency is lost at the highest orders of ppm. But actually, for the mission requirements, it's only ppm 4 through 128. So this sort of validates the transmitter performance there. We also used our flat-sat testbed to characterize the output pulse shape from the SOA, again taken here. So this shows like a ppm2 signal with a 6.6 nanosecond period that corresponds to roughly like 50% duty cycle at 150 megahertz, which is 3 times as fast as we actually expect to ever be transmitting at. And so the fact that we see sort of the full scale amplitude that we want at that high frequency also sort of validates the design we're going for. So those results concentrated on the transmitter testing. We're also looking at our pointing acquisition and tracking system, mostly focusing on the quadrant photodiode component. So for that, recently we measured the quad cell dark noise, and the power spectral density of that is shown here. In previous simulations, we got a noise figure that was actually all of our measurements are less than, and that's sort of shown in the purple. So that sort of verifies what we're going for with the analog receive chain. So to summarize the ClickBC status, the initial boards have been completed and fabricated. They're currently a part of our FlatSat test setup. We've also, I didn't get to mention this, but we've assembled the optical bench, which is shown here. So as you can see from our timeline, we've got a number of steps to go, but we're sort of on track for a launch in early 2023. I also want to take the time to mention ClickA, the initial CubeSat. So we actually finished the assembly and testing of that payload earlier this year and integrated it with the bus at BCT. And just last month, we were actually able to deliver that to NanoRacks. So we're currently awaiting launch in the summer on SpaceX CRS-25. So yeah, thank you for your attention. I'm happy to take any questions, and you can also, my email's up there. You can just email me. Oh, sure. I'm sorry, what was that? The bandwidth meaning the data rate, so 20 megabits per second is the baseline. Yes, and hopefully we can do higher, but that's the minimum success criteria. Oh, yes. On the relative velocity of the spacecraft, I don't believe we've considered that. I wasn't the one sort of doing the link budget, so I can look into that for you, but yeah, I don't believe so. Cool, well, if not, thank you so much.
All right, thank you, Hannah. And next we'll be hearing from Giovanni Pandolfi from Leaf Space.
Hi, everybody. I know it's the last presentation of the day, so I try to be fast. But of course, if you don't have any other question, just go on. So Leaf Space, you just see another presentation from my colleague Matteo. We are a ground segment as a service provider. We are based in Italy and US, but we're expanding quite a bit. So you all know what ground segment is, but typically we just connect space assets to the ground, to your mission operations so that you can actually distribute data then to your customers. We do this through 3 main services that we're running right now. The first one is Liftline. That is actually fully managed service, so we take care of everything, the ground station, orchestration, management, data delivery, baseband processing, whatever, just to deliver the data to your endpoint, but also doing uplink, of course, for TT&C. And it's multi-missions. It means that we have a network of ground stations that can be used from different missions, different customers, so leveraging the power of a network, but without paying for an actual network. And we support different frequency bands, but mainly our capacity is most on SNX, even though if we still support some lower frequencies. Also, on the protocol support, we do support CCS, DS, and DBS2, but we have one of the widest mod code support in the market, so we can also support proprietary protocols and so on. And a bunch of other stuff, but the main thing is that you can actually use the network as you want and pay for actually what you're using. And this is typically good for small constellations or single satellite missions. If instead you are ready to scale up with number of satellites and so on, maybe what you need is not a multi-mission network, is a dedicated network. And for that, we have what we call LiftKey. It's basically similar architecture as a lift line, but the antennas are actually dedicated to your mission. So you can use all the capacity available for that. And we can deploy the network according to your requirements, both in terms of frequencies, antenna aperture, baseband processing, or whatever, but also in terms of locations. So we can actually deploy and optimize the network distribution just for you. And it comes with a different price structure, so it's a fixed monthly fee, so depending on the number of stations and the type of stations, but we typically really suit on your actual requirements. And if you actually have similar requirements of what we can support with Liftline, you can also have an hybrid solution leveraging both networks and both services at the same time. A few years ago, actually, the last time that I was here, we actually started another service that we call LiftTrack that is not for satellites, but it's actually for launch vehicles. And till that time, we supported mainly all the launches that Virgin Orbit actually did, and we have contacts for all the other next launches, both from Mojave, but also for Cornwall and so on. And what we do here is basically applying a similar concept, so always ground segment as a service, but for launch vehicles, so we can deploy or ground stations at specific launch site, or use the Liftline network to support downrange reception. And this, of course, typically works for S-band, and we have real-time telemetry delivery to the launch control, and then in case we can also have auto-track capability, especially for support at launch site. All these services are based on a globally distributed network. You can see here the map. We are quite expanding, so we are actually activating 2 stations this month, so it's ever expanding. You can see that we typically go on a mid-latitude distribution to have different advantages over just polar, so we can support actually all the kind of LEO inclinations, so SSO, polar, mid-inclination like Starlink, but also equatorial. And we are expanding, as I was saying, so we will get to 23 ground stations by the end of the year. One good thing about all these services is that actually the architecture is the same for all of them. We have our unique thing that what we call the Network Cloud Engine is a set of microservices running on GCP, so Google Cloud Platform right now under Kubernetes, that actually orchestrate and manage the entire activity of the networks. And what it provides is just one single interface to the customer side, so no worries to connect to every single station for every single pass. We do that for you. We route the messages around the stations and your mission control software, and it's pretty easy and fully managed. This gives us, a lot of flexibility and scalability. So talking about the baseband, as I said, we do support CCSDS and DVB-S2. We will go to support DVB-S2X as soon as the actual market demands for it. But we are able to support also proprietary and custom protocols because we use SDRs mainly for the TT&C part, but also in some ways also for the HDR. And so we are able to, or develop by ourselves the software needed to do baseband processing, or to actually include your own software through Docker or containers in our ground stations if needed. Also, a level of abstraction is that we provide you just the transfer frames, typically both for uplink and downlink. In this way, you can apply whatever encryption or authentication scheme you want on the data before sending it to us. So in this way, you can have an end-to-end, fully secure link with your satellite. And you're not actually tied to specific hardware that we have on each ground station. So it's all abstract from your side. Let's see, okay. In terms of operations, as I said, you have just one interface. It's a RESTful API where you can both see the scheduling, you can see the logs, whatever, and then we have some real-time interfaces for TT&C and the high data rate receiving part. And as I said, one interface for the entire network. even if it's lift line, lift key, it doesn't matter. It doesn't matter if you're using the New Zealand station or if you're using the Iceland station, it's just one interface. And also we apply a zero trust architecture, so there is no key distribution between you as a user and us for the data, so whatever passes through us needs to be encrypted and authenticated from your side. So even if we have an attack, your data is not recoverable by the attacker. We are definitely ops focused. What does mean? It means that we are always open to have your input on what new features that you would like to have. We are improving quite fast. We deploy new software several times per week. So every addition that you may have that makes sense also for the entire community of our users, we can do it, deploy it, and then you can use it. We are the only commercial provider to actually support multi-spacecraft per aperture for LEO, and we are already doing it right now with time division multiplexing. We are going to have frequency division multiplexing to downlink at the same time for multiple spacecraft in the coming months. And one thing that is good to have is that we have on-call operators, so in case you have any issue with your operations, especially during LEO, but also for nominal operations, we can actually respond to your issues. And one last thing is that cost efficiency. So we built all our services to run a really high duty cycles, so we can have lower idle time, and so our own return on investment is faster, so we can have better prices for you. And we are able to do that just because we have our own way of scheduling that I will go through just in a second. And we can also do some load balancing. So even if we lose a station because of some issues with it or some other issues with the size of power or connectivity, we can actually move the capacity from one station to the other, and on your side you actually see just a change in schedule but without any loss of service level. And also in this way we can handle peak loads or other anomaly resolution that you may need in case you have something on board of the satellite. And we are able to do these two things because we do the scheduling in a really different way from other ground segment providers. So we don't let you just book passes over stations. This is not a thing that scales, really. So what we do is that we ask you to provide us mission constraints. So like how many passes per day you would like to have, their distribution along the day, any other requirements that you may have. Then we propagate your satellites over our stations. We run a scheduling algorithm that we developed, and we provide you a 72 hours moving window schedule, so you can actually know in advance which passes are you going to do. We do this because this is the only way to actually guarantee you a certain amount of capacity on a multi-mission network. So you ask for 15 passes per day, we guarantee you to provide you 15 passes per day. This is not a thing that you can do with booking because you have basically conflicting customers on the same resources. We are adding on top of that also a booking strategy, but that just works on the spare capacity to allow for some Earth observation specific needs like tip and queue or other tasking capabilities. But we always commit to guarantee you capacity with the scheduling ones. Just some numbers. So we saw that we have 3 ground segment as a service solutions, 2 for spacecraft, 1 for launch vehicles. We are supporting quite a lot of satellites. Actually, it's more than 54. It's more around 60 now. And also the launch campaigns increased. And we are already supporting 4 constellations. Some of them are IoT constellation or communication constellations. Some of them are Earth observation. And right now, we are actually already the second smallest service provider in terms of delivered capacity per day. Actually, we are just checked today, but we are the second service provider at all, not just for small satellite. And we do support all the LEO. We have 15 stations. We do a really crazy increase of capacity last year from December 2020 to December 21. We increased our capacity of 10 times, and we are going quite well also this year. And this is thanks to, of course, expanding the network, but not just that, but having more customers around it with more satellites and increasing number of satellites for that. We are the only provider with a scheduling algorithm that actually can sustain the capacity need that we have. and also the only provider doing MSPA. We are just 28 people, actually, not 27. And this is why also we are actually hiring. So if you go on our website, you can find some jobs opening. We are actually putting more and more in the next weeks. Otherwise, you can just send us an email at careers@LiveSpace. We have jobs both in Italy, but also in the US. So hope to see you guys sending us some applications. If you have any questions, just ask. Yep.
Regarding your MSPA capability, how many satellites can you have in your beam width, and then how many uplink and downlink within those satellites?
So for what we have right now, that is a TDMA, it's basically independent. It depends on how many satellites are actually flying. It's for cluster formations, basically. So with a customer that we are right now, we are flying with 4 satellites quite near together, and we are able to do that for TT&C. And it's time division, so whatever they can do, they can do. It's just a change of frequency, and it's commanded by the customers itself. So they can just do like 1 minute of contact with a satellite, then change the frequency and go another minute with another satellite, and then decide how to do that. For the frequency division multiplexing, right now we're targeting to get 3 simultaneous downlinks in X-band. This depends on the kind of receiver that we are using. We could actually move to even more, but depends on how much data actually, and also the frequency distribution of the customers that they have. So it's typically for clusters formation, not actually for having different missions at the same time. Other questions? Good. So maybe we can leave. So thanks you guys to stay so late. Hope you enjoy. And in case you have any questions, just pass to our booth. Thank you. Thank you so much.
All right, everyone. So that wraps up our second day. I hope you've been enjoying the workshop as much as I have. As always, we appreciate all our sponsors who have helped make this possible. And I hope you are able to enjoy San Luis a bit tonight. Some of the restaurants enjoy downtown, or maybe just sleep if you're tired, I don't know. Either way, we're going to start again tomorrow. Come by about 8:30 for breakfast, so you can have full bellies for our first session at 9. I look forward to seeing you then. Thank you.